ওটা বন্ধ করা হয় যে
স্যার ঢুকলে So now after a few minutes, we are going to start this technical session. So here we will have 4 speakers. So just for a practice, kind of, if you would like, you can share your screen and check whether your presentation is working fine. So, Mr. Nazir Uddin Ghazi, are you here? Yeah, thank you.
Yes, sir. Is it visible?
Yes, it's visible. And
Okay.
yes.
Thank you, sir.
Okay, so please make it a full screen, then it would be better. Okay, fine. Rana Mondal, are you here? Rana Mondal? Okay, not yet. Ansar Ghazi, are you here?
Yes, sir. Yes, sir. I am.
Could you please share your screen?
Share your screen.
Is my screen is visible?
Yes, perfect.
Okay, sir. Thank you.
And Shorup Kuila, are you here? Shorup?
I think Rana Mondal has joined.
Okay, Rana, could you please open up your screen or share your screen just to check? Rana, can you hear me? Rana, can you hear me? Okay, still we have 4 minutes more.
Yes, I can hear you.
Okay.
But Lena is, her computer says you'll be attached in a moment.
Okay.
And she's up for the next chairmanship.
Yes, sure.
But she can always come to this computer.
Okay, and maybe,
I mean,
yeah, if needed. But she can join. Could you tell her to join, connect it once again so that we can take care of that?
yes.
Okay, Rana, can you hear me now? Rana, can you hear me?
No, she's... I think her laptop says it's going to be connected, but it doesn't happen. But in the worst of cases, she can sit here and and share by my connection.
Yes, no problem.
Yeah.
Okay, Rana, just last one try if you'd like. Rana, you might have some connection issue. So good morning, Dr. Uka. How are you?
Hello?
Rana, can you hear us? Okay, so maybe we can start it now, maybe. Lena, are you here?
Du sitter just här. Pratar i min box där. Du kan säga hello.
Yes.
So I didn't get on.
Okay. But
I have to use Eric's
yes, fine.
computer.
No problem. Okay. So now we are about to start. Are you all set?
Yes.
Okay. Great. Okay. Yes, somebody raised a hand. Any issue? If you have any issue, then please, yeah. Okay. If not, then we are about to start this technical session today.
Shall I start? Yeah.
Yes,
Yes.
I will introduce you and then we will start.
Yes. Okay.
Okay. So good morning, good afternoon, and good evening to you all, depending on your location, where you are from. And welcome you all to the 3-day 15th International Conference organized by IMBIC. So in short, we call this conference as MAST, MSAST 2021. So today is the second day of this conference, and it's our great pleasure to welcome you all in the first technical session. Today, we do have a special day. So today, we organize this day is totally dedicated to a special person known as Srinivas Ramanujan. Srinivas Ramanujan is a special mathematician, is a genius from India. So India celebrates National Mathematics Day on December 22 every year. This day marks the birth anniversary of famous mathematician Srinivas Ramanujan. In 2012, the Prime Minister Manmohan Singh declared the date as National Mathematics Day to honor the great man. So we are also dedicating the whole day to this great person, Srinivas Ramanujan. With that, we are going to start our first technical session. And for this first technical session, we do have two parallel sessions, 3A and 3B. Here we are all here for 3A. And may I now request Dr. Lena Frell from Sweden to chair this session. Lena, the session is yours. Thank you.
Thank you. Welcome to this session. And before we start, I like to make you remember that the speech time is 12 minutes with questions and comments. And then I welcome Nasir Uddin Ghazi, who is going to speak about on uniqueness problem shared a polynomial with the entire function and its linear differential polynomial. Welcome on.
Thank you, ma'am.
Welcome to start.
Good afternoon. I am Nasiruddin Ghazi from Alia University, and today my topic of lecture is on uniqueness problem shared a polynomial with an entire function and its linear differential polynomial. And I am going through introduction, some definitions, previous results, our result, and some references. The basic objective of the uniqueness of entire and meromorphic functions is to determine relation between two entire or meromorphic functions when they share certain values. The uniqueness of meromorphic function starts its journey from the Nevelinus 5-value theorem. We proved that if f and g are meromorphic functions of one complex variable and f and g share 5 values ignoring multiplicities, then they are identically equal. And similarly, if fz and gz share 4 distinct values in the extended complex plane counting multiplicity, then f is equal to Mobius transformation of T. To reduce the number of shared value quickly, many authors began to consider the case that fz and gz have some special relationship. One of successful attempts in this direction was done by Rubel and Young in 1977, and they proved that for a non-constant entire function fz, if fz and f-z share two distinct finite values, counting multiplicities, then f is equal to f dash. Several authors extended the problem to higher order derivative. Here we want to study the uniqueness theory considering the polynomial shared with its linear differential polynomial. Now we have some definition. If f is a non-constant meromorphic function in the complex plane, then TRF with a characteristic function of f, which is defined by TRF is equal to MRF plus NRF, where MRF and NRF is represented by these two notation. Or MRF is called the proximity function of f and NRF is called the integrated counting function of poles of f. And any quantity is denoted by SRF if it satisfies some property. That property is that SRF is equal to order of TRF as r tends to infinity. That means SRF by TRF tends to 0 as r tends to infinity, possibly outside a set of finite linear measure. Since SRF is ultimately negligible in comparison to TRF, it is sometimes called an unimportant error term. It is to be noted that SRF does not denote any particular quantity, rather than it denotes any quantity that satisfies the above property. And now we call the function a small function if TRA is equal to SRF, then A is called a small function of f. Now let f be a non-constant meromorphic function in the complex plane C. For a meromorphic function A is equal to Z defined in C, we denote by EAF the set of zeros of f minus a counted with multiplicity, and by E bar AF the set of all distinct zeros of f minus a. If for two non-constant meromorphic function f and g we have EAF is equal to EAG, that is f minus a and f minus g have the same zeros with the same multiplicities, we say that f and g share a counting multiplicity. On the other hand, we say that f and g share a ignoring multiplicity if E bar AF is equal to E bar AG. That is f minus a and g minus a have the same zeros ignoring multiplicities. Let NRF be the counting function of zeros of f minus a in this disk mod z less than is equal to r, and if a subset of C, then the counting function NARF is the zeros of f minus a in this disk intersection A is defined as NARF is equal to intersection 0 to r NA TAF minus NA0F by T dt plus NA0F log r, where NATAF is the number of zeros of f minus a counted with multiplicities in this region. And suppose that f be a non-constant meromorphic function and a1, a2, a3 dot an are complex numbers, and then L which is defined as in this form is called linear differential polynomial generated by f. Now there are some results related to value sharing and polynomial sharing. The investigation of uniqueness of entire function sharing two values has introduced by L. Rubel and C.C. Young in 1977 in the following way. They proved that if f is a non-constant entire function and a and b be two distinct finite complex number, and if EAF is equal to EAF1 and BF is equal to EBF1, then f is equal to f1. Considering the case of ignoring multiplicity shared values instead of counting values, counting multiplicity shared values in 1979, Emius and N. Steinmarch proved the following theorem. They prove that if f is a non-constant entire function and a, b, b two distinct finite complex numbers, and if e bar af is equal to e bar af1 and e bar bf is equal to e bar bf1, then f is identical equal to f1. In 1986, G. Jank, E. Muse, and L. Volkmann, considering the case of single shared value by the first two derivatives of an entire function, they proved the following result, which is given by C, theorem C. Let f be a non-constant entire function and f be a non-zero finite number. If e bar af is equal to e bar f1, subset e bar af2, then f is equal to f1, and the following example is that the second derivative cannot be straightaway replaced by a higher order derivative. Considering higher order derivative, H-Jong extended theorem C in the following way, and he proved that let f be a non-constant entire function and a be a non-zero finite complex number if EAF is equal to EF1 and E bar AF is equal to a subset E bar AFN intersection E bar AFN plus 1 for n greater than is equal to 1, then F is equal to Fn. In 1999, considering linear differential polynomial, Peale improved theorem D in the following way, and they consider f be a non-constant entire function and L be a linear differential polynomial which is defined in 1.1 and a be a non-zero finite number, and if this condition is held, then f is identical is equal to f1 is identical is equal to L. In this paper, we extended theorem D and E in the following way. If f be a non-constant entire function and L be a linear differential polynomial and a be a polynomial with degree of a not is equal to degree of f, and suppose that a and b with these two sets where p and q are integers satisfying q greater than p greater than is equal to degree of a, and if these three conditions are hold, that is NARF plus NARF1 is order of log of TR and NBRAF1 is equal to SRF, and each common zero of f minus a and f1 minus a has same multiplicity, then f is equal to L is equal to lambda e to the power z, while lambda is a constant. If a is equal to b is equal to phi, we obtain the following corollary, and we get this expression f is equal to L is equal to lambda e to the power z. Now, if in corollary 1 a is a non-zero constant and p is equal to degree of a is equal to 0 and q is equal to p plus 1, then it is a particular form of theorem E. Also, if in 1.1 a1 is equal to a2 dot an is equal to 0 and n is equal to 1, then L is equal to Fn. And if in corollary 1.1 a is a non-zero constant and p is equal to degree a, q is equal to p plus 1, then corollary 1.1 is a theorem D. So our result is an improvement of theorem E and D, and here are some references. Thank you.
Thank you very much. And now I ask, are there any questions or comments? Well, then I thank you again for an interesting lecture. And then we go to the next person that is going to speak, and that is Rana Mondal, who is going to speak about uniqueness problem on meromorphic functions and partial pairing values.
Yes.
Welcome on.
Is my screen visible? Hello?
Yes, visible.
Okay, thank you. Good afternoon, everybody. First of all, thanks to giving me a chance for presenting my paper in this webinar. The title of my paper is on uniqueness problem of meromorphic functions and partial sharing values. Myself Rana Mondal, under the supervision of Dr. Imrul Kais, Alien University. Next, first I will discuss about introduction, next definition, next previous result, and after that our results and examples. From the beginning, Nevanlin's theory, also called value distribution theory, is a branch of complex analysis developed by Finnish mathematicians Rolf Nevanlina in 1925. Nevanlina theory studies the distribution of the roots of the equation f minus a equal to 0, where f is an entire or meromorphic function and a is any complex number. Actually, the famous 5-point theorem due to R. Nevanlina says that when two non-constant meromorphic functions taking f and g share some 5 distinct values with ignoring multiplicity, then they show that both the functions are identically equal. Actually, the beauty of this result is that there is no counterpart of this result in the real function theory. Another famous result is that the 4-point theorem by R. Nevanlina, which stated that when two distinct non-constant meromorphic functions f and g share 4 distinct values with counting multiplicity, then f and g is a mobile transformations. And these results initiated that the study of uniqueness of meromorphic functions. Actually, the study of becomes more interesting when f is or g is related to f. First, investigations began with the sharing of values from f and f dash by G. Gunderson. Next, Coronen, Halbert, and Chiang and Fang independently developed a parallel different versions of Nevanlina's theory for meromorphic functions of finite order. And this gives the directions of new study the uniqueness of f and its shift operator, f of z plus c, where c is any complex non-zero number. The next key results of these different versions of Nevanlina's theory was extended by Halbert, Coronen, and Togen to meromorphic functions of hyperorder is strictly less than 1. Next, throughout this paper, actually first we discuss about the small functions. So we first consider a meromorphic functions f, which is obviously non-constant, and meromorphic obviously in whole complex plane. For such a meromorphic functions f and taking a complex number a when the term TRA equal to order of TRF holds when r tends to infinity, possibly exceptionally set of finite logarithm measure, then we say that a is a small functions of f, and all of these small functions of s is denoted by sf, and taking to term infinitive in additions, then we write s infinitive f. The value distribution theory of Nevanlina is about a century old and still is an active area of research. It has a wide range of applications within and outside of functions theory. Recently, many authors have focused on the value distribution theory in different analogs, such as differential operator, Nevanlina's characteristic of shift, differential polynomials, or analog of logarithm derivative, and a lot of contributions in the development of such things, and making a constructed excellent work and studying the sharing value problem. First of all, I will introduce about the definitions. The definitions one is that first we taking a non-constant meromorphic functions f, and we define to the order and hyperorder of the function f, which is specified by rho f, which is denoted by limit sup of log plus the characteristic function of f upon log r, and hyperorder is that limit sup log plus the characteristic function of f upon log r. Next, the definition 2 is that for a non-constant minimum function f and taking a small functions az in the extended complex plane and k is any positive integer, we define a set E bar less than equal to kaf as a set of distinct a points where its multiplicity is less than equal to k, and obviously taking a points is counted only once in the set. And next, if k equal to infinity, then we neglect the term of k and we just denoted by E bar af. Next, the counting functions of the distinct points a of f with multiplicity less than equal to k is denoted by n bar less than equal to k r a f. And also similarly, we can define n bar greater than equal to k, and the set is defined E bar greater than equal to k a of f. Next, definition 3. What is the IM and CM? Now I define about the definition of CM and IM. First, let f and g be two non-constant meromorphic functions, and taking a complex valued function in the extended complex plane, say a, the zeros of f minus a and g minus a coincide in locations and multiplications, then we say f and g share the value a cm. And if taking a equal to infinity, the zeros f minus a and g minus a are taking poles of f and g respectively. And another, if we coincide the locations only, just neglecting the multiplicity, then we say that f and g share a as a IM. So by the above definition 2, we say that when the set E bar af and E bar az are coincide, then we say that f and g share the value a with IM. And when we neglect, we just neglect the bar and taking EAF and EAG are coincide, then f and g share the value a as a CM. Next definition is the definition number 4, which is more important in our paper, is that which is the introduction to K.S. Charok, R.J. Koronan, and Gaurav Kumar. They say that when taking first a meromorphic functions f and share a function az partially with another meromorphic function gz, when the inclusion relations, the subset relation E bar af subset of E bar az holds. When this inclusion relations holds, we say that the meromorphic functions f share the function f with gz. The next definition is that definition of 5. Suppose f and g taking two non-constant meromorphic functions and taking a as the belongs to SF intersection SG in the extended complex plane, and we define n bar c RAF G, which is the common a points of f and g in the disks of mod z less than r, which is obviously counting only one point in the set, and we denote this n bar fj RAFJ equal to the counting function of the point f minus a plus counting function of the point g minus a and minus 2 of the common a point of f and g. Actually, n bar fj RAFJ actually the different solutions of f minus a and g minus a. And next definition is that the deficiency values of a point a in SF with respect taking so definitions of a with respect to meromorphic functions f as defined as follows: as delta f equal to 1 minus limit of the counting functions of f minus a upon the characteristic functions of f itself. Next, I will discuss about the previous result. So previous result is that first of all, a periodicity problem, we have defined the Huntington's, Koronen, Lane, and Repo in the year of 2011 have considered a value sharing theorems for shift of meromorphic functions and obtained a beautiful result. The result is that let f z be a non-constant meromorphic functions of finite order, obviously, and c be a non-zero complex number, and let three distinct periodic functions a1, a2, a3 in the small functions of in the extended complex plane. If fz and its shift share three periodic function with Cm, then they prove that function and its shifts will be identically equal for all z belongs to C. And next, theorem is that in 2009, the same authors, together with Jie Zhang, in the reverse work 2009, improved the assumption 3cm to 2cm plus 1 im and proved the following important result. The same result, but they proved in the case of 2cm plus im. So F be a non-constant numeric functions of finite order and C be a non-zero complex number, taking three distinct periodic functions with periodicity C, and if F and its shift share two values A1, A2, Cm and A3, Im, then they prove that the function is a periodic function, such that F and its shift will be identically equal. Next is the important result regarding the periodicity functions, which is proved by SZ Chen and WC Lin in the year of 2016. They actually prove the same result with using the Wigner restrictions, the hyperorder. So we make into next example and obtain the following result. The following result is that fz be a meromorphic functions, obviously non-constant, and hyperorder less than 1, and C be any non-zero complex number, taking three distinct periodic functions A1, A2, A3, if F and its shift share 2cm plus 1 im, then they prove that F is a periodic function, or F and its shifts will be identically equal. And so next, returning to the case of sharing three values, we know that actually the problem of 1cm plus 2 im and 3 im has been left open for a long time. And now it is in 2016, R.J. Chorok, R.J. Koronen and Gaurav Kumar introduced a notion of new different parts of partial sharing values. And they obviously prove that the functions will be, function is a periodic functions when they share 1cm plus 2 im or 3 im. Next, they prove that is an important result, just taking a combined result with an under approximate deficiency assumptions. The result is that let F be a non-constant meromorphic functions of hyperorder less than 1 and C be any non-zero complex number, taking four distinct periodic functions A1, A2, A3, F, and taking extra conditions, which is the deficiency assumption delta AF, which is obviously positive for some A in SF union infinity, and they taking E bar AIFZ, subset of E bar AIFZ plus C. This is the partial sharing. Then they prove that function is a periodic function. And after that, in 2019, W. Lin proved that the important same result, but they share just three distinct periodic functions A1, A2, A3, and taking another part at most finitely many poles, and they prove the same result. F is a periodic function. And okay, so now
That your time is out.
okay, now we to our result. Now we discuss our result. Our result is that first aim is that to deduct and rectify by conducting the deficiency conditions and assuming the functions the f and z and each shift of f and z plus eta, where n obviously is a positive integer, and taking first f be a non-constant number of functions of hyperorder less than 1 and eta be a non-zero complex number, and taking n obviously positive integer, and we share f and z plus eta four values partially. Then we prove that function and its shift, the quotient of function and its shifts will be the constant term. So f of z equal to lambda f of z plus eta, where lambda satisfy the conditions lambda triple n equal to 1. And we first taking example.
Dana, your time is
out.
So please, within 1 minute, please conclude.
Okay, so okay, thank
Yes,
you,
I
sir.
give you 1 minute, but not more.
Okay, thank you. So that's example 13. Example 13 is proof that we can, our example is true, and the example 14 is so that we cannot extend the 4 partial cm to 3 cm, then the result cannot be whole. Theorem. The next result is that when the conditions of theorem 12 partial shares values can be transformed to truncated partial shares values with a positive integer k. And we just proved that if the non-constant numeric functions and taking for distinct values. If we share partially, we tanker it up to level k. When k greater than equal to n, then we prove that fz equal to lambda f of z plus eta, where lambda satisfies the conditions lambda to n equal to 1. And next, this is my reference. So thank you.
Yes, thank you for an interesting lecture. And are there any comments? If not, I thank you again for an interesting lecture, and we go
Okay, thank you,
next
thank you.
person.
Stop.
And now I call Ansar Ghazi about
Yes, ma'am.
common fixed point results of 4 weekly compatible mappings in modular metrics. Will you please I take it again. Who is going to talk about common fixed point results of 4 weekly compatible mappings in modular metric spaces? And welcome on.
Thank you, ma'am. Good afternoon to all of you. Myself, Ansar Ghazi, a research scholar of Department of Mathematics and Statistics of our university. Under the supervision of Dr. Sumanapal, paper of my presentation of my paper is, title of my paper is Common Fixed Point Results of 4 Weekly Compatible Mappings in Modular Metric Spaces. Outline of my presentation is like this. Actual fixed point theory is a rich, interesting, and exciting branch of mathematics, and it is very an important area in the fast-growing fields of nonlinear analysis and also nonlinear operators. And fixed point theory mainly useful in the existence theory of differential equations, partial differential equations, integral equations, etc. And it has many fruitful applications in eigenvalue problems as well as also boundary value problems. The study of common fixed points of mappings satisfying a certain contractive condition attracted many researchers. And first of all, the concept of commutativity has generalized in several ways. For this, in 1982, Sesha introduced the concept of weakly commutative maps. Then Jung generalized this idea first to compatible maps in 1986 and then to weakly compatible maps in 1996. In 1998, Jung and Rhodes further started the notion of weakly compatible maps. In 2010, first, Jiskakov introduced the notion of modular metric spaces, and he first presented some interesting applications for superposition operators and by applying theory of modular metric spaces. Later, researchers have studied and extended fixed point problems in modular metric spaces. In this paper, we proved some unique common fixed point theorems for 4 weakly compatible mappings in modular metric spaces without using the notion of continuity. Also, we further deduce some unique common fixed point results of 3 mappings and 2 mappings and give example to illustrate our main results. Actually, our results generalize and extend the results of Roimpur. In 2010, Jiskakov introduced the definition of modular metric space like this. Let X be any arbitrary set, a function omega from 0 infinity to x plus x to 0 infinity is said to be modular on X if it satisfies these 3 conditions: omega lambda xy equal to 0 for all lambda greater than 0 if and only if x equal to y, and omega lambda xy equal to omega lambda yx, and omega lambda plus mu xz less equal to omega lambda xy plus omega mu yz. If instead of the first inequality, if omega satisfies this only, omega lambda x is equal to 0 for all lambda greater than 0, then omega is said to be pseudo-modular. And omega is said to be strict modular if it satisfies there exists a lambda greater than 0 possible depending on x and y such that omega lambda xy equal to 0, then x equal to 0. And also this modular is called convex modular if instead of third inequality, it satisfies this inequality. Omega lambda plus mu xz less equal to lambda by lambda plus mu omega lambda xy plus mu by lambda plus mu omega mu yz for all lambda mu greater than 0. And also here, omega lambda xy is always non-increasing function on 0 to infinity. Here, just two sets x omega and x omega star. X omega is defined is like this: x omega x not equal to x belongs to x such that omega lambda x not tends to 0 as lambda tends to infinity. And also x omega star is this: there exists a lambda greater than 0 such that omega lambda x not less than infinity. These two spaces are called modular metric spaces around x naught. In general, x omega x naught proper subset of x omega star x naught. But if omega is convex, then these two are equal. X omega x naught equal to x omega x star x naught. Next, there are some definitions. A sequence xn in the space modular metric spaces is modular convergent or omega convergent to an element x belongs to x omega if there exists a lambda greater than 0 possible depending on xn and x such that limit n tends to infinity omega lambda xn x equal to 0. Also, this sequence is said to be modular Cauchy or omega Cauchy if there exists a lambda depending on the sequence positive lambda such that limit mn tends to infinity omega lambda xn x equal to 0. And the modular space x omega is said to be modular complete if every omega Cauchy sequence from x omega is omega convergent. Also, any subset m of x omega is said to be omega closed if the omega limit of any convergent sequence of m is in M. There are some examples. Yeah, if x be any metric space with at least two elements, and we let for all xy belongs to x, omega lambda xy equal to dxy, then this omega lambda xy satisfies all these three inequalities, and this is also a modular metric space, and this is not convex because if we take z equal to y and mu equal to lambda, then the third inequality is not satisfied. And next one, omega lambda xy equal to dxy by lambda for all lambda greater than 0. This is also modular metric spaces. And also omega lambda xy equal to this dxy by lambda plus dxy for all lambda greater than 0. This is also modular metric spaces, but this is not a convex modular metric spaces. Next, x omega be any modular metric spaces, then metric convergent implies modular convergent. That means limit n tends to infinity d omega xn x equal to 0 if and only if limit n tends to infinity omega lambda xn x equal to 0 for all lambda greater than 0. Also, there is another condition: a modular lambda, a modular omega on x is said to be delta 2 condition if for any sequence xn and x belongs to x omega, there exists a lambda greater than 0 possible depending on xn and x such that limit n tends to infinity omega lambda xn x equal to 0 implies limit n tends to infinity omega lambda by 2 xn x equal to 0. And this implies limit n tends to infinity omega lambda xn x equal to 0 for all lambda greater than 0. But in our paper, we assume omega is always satisfies delta 2 condition. And Roempel define coincidence point and weakly compatible maps in modular metric spaces like this. If we take take two mappings h and t from x omega to x omega, the point x belongs to x omega is said to be coincidence point of h and t if tx equal to hx. And also h and t are said to be weakly compatible maps if they commute at their coincident points. Also, Roempel proof two maps fixed point results t and h have a coincident points if these two mappings satisfying the following condition: tx omega subset of h omega, where h omega is a omega complete subspace of x omega, and there exists alpha beta gamma belongs to 0 to 1 such that the following three conditions are satisfied. First one is if alpha plus 2 beta plus 2 gamma less than 1 for all alpha beta gamma less than 1, and number 2 omega lambda tx ty less equal to alpha omega lambda hx sy plus beta into this plus gamma into this, and number 3 is omega lambda hx ty less than infinity, then t and h have a coincident point. Next, our main results. First, we prove this x omega be, let us consider x omega be any complete modular metric spaces, and we consider four maps f, g, h, and t from x omega to x omega, and satisfying the following conditions: omega lambda hx ty less equal to a1 into this plus a2 into this plus a3 into this plus a4 into this plus a5 into this, where every ai greater equal to 0 are real numbers, real constants, and with a1 plus a2 plus a3 plus 2a4 plus a5 less than 1. And also if fs and gt weakly compatible maps, then and tx omega subset of fx omega and sx omega subset of gx omega, then f, g, h, and t have a unique common fixed points in x omega. Another theorem is, if we consider these four maps and satisfying this inequality, a into this, b into this, plus c into this, and satisfying this, and if the pairs fs and gt are weakly compatible, then these four mappings have also unique common fixed points in x omega. Next, there are some corollaries. Three maps fixed point. If we consider here g equal to f in the previous theorem, then you will get the triangle inequality becomes omega lambda sx ty less equal to a into omega lambda fx pi plus b into omega 2 lambda fx sx plus omega lambda fy ty plus c into omega 2 lambda fx ty plus omega 2 lambda fy sx, where a plus b 2b plus 2c less than 1. And if the pairs fh and ft are weakly compatible, then the three maps f, h, and t have a unique common fixed points in x omega. Next, two maps result. If we consider g equal to f equal to identity map, then we will get two maps result. Another theorem is, if we here only one, if we replace g equal to f equal to I and s equal to t, then you will get these results, omega lambda tx ty less equal to this, and here finally we get t has a unique common fixed points. Next theorem is that if we consider here we consider four maps f, g, h, and l, and satisfying this condition, lx omega subset of fx omega, hx omega subset of gx omega, and satisfying omega lambda hx ly less equal to k into maximum of omega lambda fx gy, omega 2 lambda fx hx, omega lambda gy ly, and half of omega 2 lambda fx ly plus omega 2 lambda gy hx for all xy belongs to x omega, where k is less than 1 and positive, and assume that the pairs lg and hf are weakly compatible maps, and if one of fx omega or gx omega is closed subspace of x omega, then the four maps have a unique common fixed points. Here also we derive from this result three maps fixed point theorem. If we put g equal to f in this previous theorem, then you will get this result corollary, and here we f, h, and l have unique common fixed points, and the inequality becomes this. And next corollary, if we replace g equal to f equal to identity mappings in the previous result, then we will get this corollary. Here inequality becomes omega lambda hx ly less equal to k into max of this, and this, and then h and l have a unique common fixed points in x omega. And also another corollary, here if g equal to, we consider g equal to f equal to I and h equal to l equal to t in the previous theorem, then you will get this result, omega lambda tx ty less equal to k into max of this, and here t has a unique common fixed points. Also there is a supporting examples for our theorem. Here we consider x omega equal to closed interval 0, 1, and the metric modular omega is defined by this, omega lambda x y equal to mod x minus y, and define fj on x omega like this, fx equal to this, tx equal to this, hx equal to this, and gx equal to this. And here clearly tx omega subset of fx omega and hx omega subset of gx omega. And here omega lambda hx ty equal to this, less equal to this. Here all the coefficients are here a1, a2, a3. Their sum is also less than 1. And tx omega, hx omega, fx omega, gx omega is here close subset of x omega. And clearly tx omega subset of fx omega and hx omega subset of gx omega. And here fs and gt are clearly weakly compatible maps. And also it is in that here 0 is a common fixed points of all the four maps. And next, these are my references. Thank you.
Yeah, thank you for an interesting lecture. Any comments or questions? Then I thank you again for an interesting lecture, and go to the next speaker, that is Swarup Koila. He's going to speak about a note on generalized derivations on non-control Lie ideals in prime rings. Welcome on.
Thank you, madam. Am I audible? Actually, madam, I am here, but I'm unable to share my screen actually.
Go see.
Okay, could you please, can you see a box, arrow box?
Yes,
at the
sir.
bottom? Yes. Could you please click on that?
Yes, I clicked.
Can you see your entire screen?
Yes, that I also clicked before.
Okay, then you can see a black box and share and cancel. Both are there.
Yes, but yes, sir. It's
Yes,
share,
click on that box, black box. Click on that black box.
but share box is not working, sir, right now.
No. Click on the black box, not on share or cancel.
Okay, yes, sir. Yeah, I got it. Yes, thank you, sir.
Okay.
Okay. Okay, sir.
I got you, sir.
Min har inte kommit in på hela tiden. Annars hade jag kunnat gå
Is my screen visible, sir?
Yes, please make it a full screen.
Yes, sir. Is it fine, sir?
Yes, great. Okay, thank you.
Good afternoon to all respected dignitaries and my researcher friend all over the world. Today is a glorious day, as Professor Odhikari mentioned earlier. It's my pleasure to be here on such kind of glorious platform indeed. Today I'm going to present a topic entitled with a note on generalized derivation on a non-central Lie ideal in prime ring. I am Saurabh Koila, a senior research scholar from Jadavpur University, Kolkata. This is my outline. My outline contains introduction, some motivation, and then I included main work and some bibliography will be there. Ring derivation is a branch of algebra in which we study about the structure of an additive map as well as the structure of a ring by analyzing some functional identities involving additive maps. These additive maps are derivation, skew derivation, generalized derivation, generalized skew derivation, degeneralized derivation, multiplicative generalized derivation, multiplicative bracket generalized derivation, etc. It is well known that there is a strong relationship between the functional identities involving derivation and generalized derivations and the structure of rings. In this paper, we try to find out the structure of some generalized derivation satisfying a functional identity on a Lie ideal of prime rings. Here is some notation which will be frequently used in my work. Throughout this paper, I will consider R being a prime ring, and as we know, it is a very basic thing. What is prime ring? And the center of R is considered as ZR, and U is the atomic quotient ring of R. It's a very good super ring of R. It has tremendous properties and real correlation with R. For timing, lack of timing, I did not mention here. And see the center of U. It's called extended centroid of R. And for a prime ring, it forms a field. And Lie bracket of x comma y will be defined as xy minus yx. It's the simple commutator of xy. And in my paper throughout, I will read as simply just commutator of x comma y. And store the standard polynomial identity in 4 variables and defined like this way. And M and K, the ring of all n by n matrices over a field K. There is some basic definition which is used here. Definition of derivation. Derivation is nothing but an additive map from D, derivation D, a map from R into itself is called derivation if d of xy equals to dxy plus x dy whole for all xy in R. Now, if we take dx is simply just commutator of a comma x for some a in R, then you can easily check that it forms a derivation, and this type of derivation is called inner derivation. Professor Resser introduced the notion of generalized derivation. Generalized derivation is an additive mapping from f of f into R itself. It's called a generalized derivation if there exists a derivation d of R such that f of xy equals to fxy plus x dy holds for all xy in R. Here, we read it if is generalized derivation associated with the derivation d. Like the previous case, if we take fx equals to ax plus xb for some ab in R, then we can easily check that f forms a generalized derivation with the associated derivation dx equals to minus commutator of b comma x. This type of generalized derivation is called inner generalized derivation. here is an important remark. In the definition of general derivation, if we saw that there exists derivation D, and this derivation may not be unique in general, but if we consider R is unique, then this derivation must be unique. Sorry, if we consider R is prime, then this derivation D with of this general derivation must be unique. And here some definition of commuting and centralizing mapping on S. A mapping D from R to R is called commuting on a subset S of R if commutator of dx, x equals to 0 for all x in R S. And this one map is called centralizing if commutator of dx, x in ZR for all x belongs to S. Now the definition of Lie ideal. It's an additive subgroup L of R is said to be a Lie ideal of R if commutator of L, R is subset of L. Here is also an important remark. We can easily say that from the definition of ideal that every ideal definitely satisfies this condition. So every ideal will be Lie ideal, but the reverse is not true in general. Here is an example of generalized derivation. If we consider the ring R like this way, and define the map like this way, and if we define a derivation, we can easily check that this from D forms a derivation. Then we can verify that this map F will form a general derivation associated with the derivation D. But if we can calculate proper way, then F will never be form a derivation. So the concept of general derivation covers both the concept of derivation as well as the general derivation. Here is some motivation from where I motivated to do my work. Professor Carini et al. In 2010, they did some work. They studied on this identity basically. What they did, they studied this identity on a prime ring characteristics different from 2, and they considered L a non-central Lie ideal of R, and they have taken G and H to non-zero general derivation, and they studied this identity. And then they got the structure of G and H. What did they got? They got Gx equals to C dash x and Hx equals to B dash x plus xt dash, where B and C in U with the condition A B dash equals to 0 or R satisfies S4, and Gx equals to C dash x, and this type of thing result they found. And in 2011, Professor Nutgan Argak and Professor Francisco de Filippis, they did this. They studied this identity on a ideal where they have taken fxx minus xgx, where f and g are both non-zero general derivation, and f and x belongs to fi, the involution of f on the ideal I, where f is a non-central multilinear polynomial. And in 2014, Professor Francisco de Filippis and Professor Basudev Thada, they studied the previous case on the central in center. What they did is that they have taken I as a non-central right ideal instead of taking the ideal, and they also got some phenomenal structure of G and H. Very recently, in 2017, Professor S.K. Tiwari and Professor R.K. Sharma, they studied the condition FUGU minus UHU, where F, G, and H are non-zero general derivation on R, and U belongs to FR, where F is a multilinear polynomial, and they also find out the tremendous structure of F, G, and H. Motivated by the above works, here I studied the following key situation. Let R be a prime ring with characteristics different from 2, U be the U2 ring of quotient, and C equals to ZU be the extended centroid of R. And if I consider L be a non-central Lie ideal of R, and F, G, H are 3 non-zero general derivation of R, and if the commutator of FUGU minus UHU equals to 0, then for all U belongs to L, then we got the structure of F and G in the following way, where the first case was that Fx equals to Ax, Gx equals to Cx plus Sq, and Hx equals to Px plus Xp dash, where A, C, Q, P, and P dash from the U2 ring quotient, and these elements have the following relations. And the second, if fx will be like that, xa and gx will be cx and hx will be px with this condition of this ac minus p in c. Or here I got that fx will be like mu x and gx equals to cx plus lambda hx and hx equals to px plus hx, where h is a derivation and p and c from mu to be ring quotient ring, and lambda and mu belongs to the extended centroid with the condition mu c minus p in the extended centroid and lambda mu equals to 1, or R satisfies S4. And then we immediately got the corollary. If we consider gx equals to x, then you can easily check that this can be easily checked that this forms a derivation, general derivation. And then I got the special case which was studied by Professor Vincenzo De Filippis and Renia in 2010, and they got this result. And which actually my result is the extension of their work. And the corollary 2, if I put h equal to 0, then I got the corollary which was studied by Professor Carini, De Filippis and Scudo in 2020, and the corollary is like this. And these are some references which I used to do my work. Thanks a lot for your kind attention. And if
thank
there
you.
any
And thank you
question,
very much.
thank you, madam.
Interesting lecture. And are there any comments or questions? If not, I thank you again for a very interesting lecture.
Thank you, madam. Thank you.
And that ends this session. And I thank you all participants for an interesting hour.
Thank you, Dr. Lena Trell, for chairing this session. And on behalf of this organizing committee, I thank all the speakers, the 4 speakers, for their excellent presentation, as well as Dr. Trell for chairing this session. So now we will quickly move on to the next session. I can see that Professor Fatukun is already with us, but I think he is on the transit, but he will be soon to his position from where he will be able to deliver his presentation. So may I know? Yes. So yes, please be at your place from where you will be able to deliver the presentation. We are waiting for you. No, don't worry. So we will reshuffle the presentation ordering. So first, Professor Trail will be delivering the lecture. He is already here. Shubhra Bhattacharya, are you there? Shubhra, are you here? Shubhra Bhattacharya, are you here? Yes, I can see her name.
Yes, I'm here. I'm here.
Okay, great. And I get one email today from Professor Ravinandar from Tripura. Actually, he is currently suffering from COVID, so he won't be able to deliver his lecture. We wish a very early, quick recovery for him. And instead of that, I get another request from one of the students who wants to give his lecture early session, so we can switch him in this portion. And the last speaker would be Gulsum Uka from Turkey. Are you here, Gulsum? Gulsum, are you here? Can you hear us? I can see Gulsum.
Yes, yes, I hear you.
Okay,
Thank
great.
you.
Yes,
I'm
great.
here. I'm ready for you.
Okay, so the ordering could be first, may I request Professor Eric Trell, and then Dr. Shubhra Bhattacharya, then Professor Gulshan Uka, and then I guess Professor Fatukan will be back to his position so that he can present, and at the end the student will deliver the lecture. Okay, so now may I
thank you. Hopefully I should.
Yes, sure, no problem. Yeah, please.
Okay, thank you.
Yeah, so may I now request Professor Eric Trell to share your screen, please? Professor Trell?
Yes, I'm on. I hope you hear me.
Yes, I can hear you. Could you please share your
Yes.
screen? Yeah.
And I share my screen
Yes.
because it's full with the presentation.
Okay. So can you go to the Google Meet one? Can you see your image? Can you see?
No, I don't see it because the screen is full of the presentation.
Okay. So maybe on the browser, can you see the browser at the bottom of your laptop?
No, it's simply full by the. So I have to get out, escape to be able to. So no,
Yes.
I'm on the screen, but
Yes.
I would like to present it.
Okay.
In a kind
So
of.
can you see a box with an arrow, up arrow with a box at the bottom, not at the top, at the bottom of.
At the bottom.
Yes. An
Yes.
up arrow with a box within a box. Can you see that?
No. What did you say?
It's just an arrow. Can you see all the the videos, the telephone sign and all at the bottom of your screen?
Yes.
Can you see your image on the screen?
Well, I know I'm in here, but I would like to go on with presentation. But
no, unless you share your screen.
No, I'm in. Yes.
Okay.
But then I lost my presentation.
But that will come soon. That won't be a problem. But first share your screen first. Okay.
Yes.
So can you see a arrow with a box? An arrow within a box?
An arrow in a box.
Arrow.
A pil in a
Yes,
box.
yes, I see that arrow.
Please
Yes.
click on that.
Tryck på den.
Yes.
Yes. Yes, on that.
Can you see now your entire screen? Your entire screen?
Yes.
Please click on that.
I'm pressing on that.
Very good.
I'm
And
pressing on that.
yes, then can you see a whole box of your screen? So a box.
You can't share this.
No.
And
so please click on
an
the
error. It's an error that has happened.
error. So you are from Chrome, Google Chrome? You are from Google, using Google Chrome?
Yes. But I have to have, yes. I think I have to have, I think I have to present my presentation like this.
No, then we won't be able to see your screen.
No, I know.
But can you please just click on that, on the image, on a
Can you see the screen now?
No, not yet. So can you press on that box where your image is showing on the screen? A black color box, big box.
Yes. But yes, I know the big box, but I mean, no, I have an error within a box, yes?
What it says?
Arrow within a box. And I present all the screen.
Yes, and then a box will come.
And what it comes to me, it is not possible to share the screen.
I think you are not using Google Chrome. You are using maybe.
Yes.
What are you using? If you are not.
It worked before. But why can I not present the yes. Yeah. It was an error that was happening.
No, is it? Can you please check? Is it Google Chrome? If it is not Google Chrome, then it would be a problem for Mac. So you are using Macintosh?
Yes.
And you are not using Google Chrome, then it will show you error.
December. Present now. Dela hela skärmen, presentera. Det går inte, you can't ignore Google Chrome.
I have a suggestion. I mean, can you just try with Lena's computer? The same.
Yeah, but then I don't have the presentation.
Oh, okay.
Sorry.
So are you using Google Chrome? Are you sure?
I think he has gone. He will again rejoin.
Maybe, yes. So maybe we can wait a bit. Otherwise, we will start the next speaker and he will again join us with this.
He has joined again.
Yeah. Yes, done. Thank
Now
you.
it's working. Now it's working.
Perfect.
But you need to unmute yourself.
Please unmute yourself. Yeah. Not yet done. Not yet done. Please unmute yourself. You haven't done it.
Click that.
You need to minimize the presentation and then. Yes.
Yes, first unmute.
Yes. Yes, great. No, it's already presented. You are presenting. Please don't do anything.
No, don't stop that. Don't stop that.
You're already presenting. Yeah.
Yeah, just open your slides and you can start.
Yeah.
Yes, great.
Yes.
So make it full screen. That's all.
No.
Yes.
Like now. Yes. And should I then take full screen or
Yes,
just go by this screen?
Yes. Now we can hear you. You can also hear us.
I see. Yes. So I see whether I take bildspel. Then I shall make it rapid presentation. Now we shall see. Do you hear me now?
Yes, perfect. Thank you.
Okay.
So yes,
so I can start.
So you started late, but yet still we have 30 minutes for you.
Yes, 30 minutes. Yes. Well, so this was a bit of a problem, but I speed up. So my title you can see here, and it's going to be clear in the end, I think. I'm going to talk about Mario Sophus Lees work and his thesis over en klasse geometriska transformationer. A class is a kind of anticipation of a group concept, but it's a class of geometrical transformations. And the idea is instead of the point as element, use the straight line of length equal to 0. So that is very important. And he was about the same time as Mendeleev, and that was 1871. So it's 150 years ago. And it started 2 years earlier by his, you could say, replacing the imaginaries plus and minus I by geometrical planes and lines. So he brought complex space to real Euclidean space. So he immediately introduced linear algebra, and that is one of his creations. But he didn't stay with the two-dimensional plane, but he went to the three-dimensional and the eternal question about the difference between a cube and a square. And you can say that he made a kind of phase transition from the Euclidean space to the spherical space. So it's a kind of curvature, and you can say that you can go from the most extended to the most compressed form of unit and you can't go further than the sphere there. So it's a kind of abiding dark mass, you can say, and proportionally it is very much in that size. Anyhow, you can't do it with a bang, so to say. You must do it with a kind of matrix. And that means that this idea is not at all a big bang, but an isotropic idea. So it's made evenly throughout space. Whereas Gell-Mann used the point concept and rotations in Lie group. The idea here is instead to see on the sphere itself and combine X, Y, Z Euclidean space with the A2 root space diagram of SU3, and then making it kind of real, so to say. And then you have two aspects of this. You can make your ideas and calculations on the sphere and its surface and its interior, but you can also come out, because in this way we have created a three-dimensional lattice instead of a flat diagram, which can't really form a spatial structure at all. So I just rush through this and see that if we combine the root space vectors here, they form kind of 120-60 diagram lattices, but we also have 180 and 90 angle connections here. So he's doing a kind of transformation from the flat to the spherical, and that's scale independent, you can say, but he does it on the infinitesimal sphere. And then you can make it gradual, or you can make it stepwise and develop kind of minor and major semi-axis. And this is the kind of interior transformations that open up with the Lie idea. And for instance, if you make systematic stepwise transformations of the major semi-axis, you end up with ellipsoid transformations that are volume and symmetry preserving. So it has the gauge and flavor invariance of quantum chromodynamics, but in a geometrical instead of a unitary representation. And if you make calculation about the mass content, so to say, of the contracted semi-axis according to quark pressure formula, you come up with very, very close correlations with observed data. I don't go into that. I show another slide that if you study the interior symmetries of the sphere, infinitesimal sphere, you find the baryon transformations, you find the mesons as a kind of differential coils in between, and you find all kinds of, depending upon the kind of collision energies and scattering energies, you can find all kinds of compressions that give you increasing mass values. So this is virtually the whole standard model. And if you have sufficiently high energies, you come to disrupting the sphere, and that could be by the gauge vectors that it contains just being released, or that could be by the gluon, the 8 gluons. They come to a burst, a 3-jet event, and release their jets out to space. In each corner there are 8 gluons, and even if you smash the ball just like a clap of your hand, it bursts in the sides and sends out the top quark, as it is called. But anyhow, you can recall all the standard model symmetries. And I go specifically now to these connections, which I showed you earlier, that could be 180-90, and it forms helicoidal or spirals or just orbits which when you measure their length in relation to the proton radius comes out with a mass value of the muon. So this should be the muon, which is the kind of straight. But if you connect the 120 angles network size, you can't really make it stay, but it leaves. And if you measure the mass content of this, it corresponds very close to tau. It's all in that here. So I just go through the principles. But the important principles of tau is it's a line connection that doesn't stay in the nucleus but goes outside. And in effect, that is called a nuclear electron. And it is actually the start of an electron which comes outside of the sphere, because it doesn't actually is included in the standard diagram. Standard diagram doesn't contain a representation of the electron, but it has the tau as a kind of internal electron. And when it has to leave, so to say, the electron, the proton nucleon, it continues as electron, as we shall see. I just show you here some other decays, gamma decays from P0, and also I show you a muon, for instance, how that can bend into an electron and then leave an anti-neutrino and neutrino, respectively. So just showing you the correlations that the system. But the interesting thing is the root space vectors going out of the sphere. And then if you connect them, they form a kind of structure of one octagon and two tetrahedrous, octahedral tetrahedrous that goes directly to isotropic vector matrix lattice. That is, of course, universal because it's endless, and you can now try to find a non-overcrossing way to filling space without colliding. And then you have to use the chaperone principle of space boxes and Euclidean space boxes and the kind of lattice structure you hear here. And you find this kind of structure that illustrates how you should pack them in order not to collide with themselves and be able to fill universe, so to say, from the starting points. And interestingly, you find that one self-packing constellation is the Bohr orbital, and it's giving you the kind of packing you need, so to say. But this is only the bottom plate, and we need to have a kind of cap also. I should come back to that. What is causing the cap, so to say? Well, that is horror vacuum, you could say. It's filling itself. Anyhow, this just summarizes the kind of ideas here, that we do have a kind of wave packet, which of course is Schrödinger idea from the start. So we build a little model of it, and you see that it fits like a jigsaw in a kind of larger structure, and we can make combinations of it. And we can see that here we have the cap. We fill the cap, and we have the bottom plate, and it brings us in all 153 times 12, 836. This is proton-electron mass ratio. And we can, by this, tessellate, because it complements with these corners, the space totally, so that it even doesn't give place to a stepwise development. It reminds very much of a ribosome, large subunit, a small subunit, a bottom plate, which etches, so to say, the structure, and a large subunit that clips about creating the complete structure. I don't go into this. I just show you some models here. And we have, of course, the bottom plate, and we have the cap, and we combine it, and we can build of it. Anyhow, this will obstruct space. You can't make any steps with it. So we make instead another construction here. We take two tangentially colliding modules, and we see that they form a triangular kind of system here, which also is a module with a roof, as it were, if we can construct that. We go on just seeing the construction that if we have the roof on, we have this cross section. I won't go into that, but it's a kind of structure here which has a kind of the package cells and the kind of wave cells, and that can be combined in various ways. And we also see that when the walls here are rupturing, there can be gammas and neutrinos if there are straight lines or curved lines. So this will be clear. We see the construction principles that we can have here, for instance, deuterium, which is deuterium because it's coiled here. And then we have tritium. But if we have instead a kind of wave package, wave structure, wave triangle, we have 2 helium-3. And we have the combined deuterium, we get the helium, the ordinary helium atom. So we can go on unpack space, and we soon find that we have to have some simple representation, because these detailed kind of Lego pieces are going to be blurred. So here we have combined the kind of illustrations. We have both the Lego type and we have the Duplo type, but we show they are space filling. That's interesting. They are space filling. And if we go on just with the Duplo kind, we see that they fill space very nicely. And we can go on, potassium, calcium, scandium, titanium, vanillin, and so forth and so on. So we come to iron, and now the burning process is stopping. And we can see that the kind of atoms we create, they can be jigsawed to each other and form molecules. And they can be smaller and larger and combine carbon tetrachloride and potassium and so forth and so on. I just go on. After iron, we have to use another mechanism, and that is slow neutron capture. So it's if we have an XX neutron, it can be mobilized and pressed into a kind of combination where it combines to deuterium then, because it becomes loaded. So it will be increased in not volume but in atomic number. And for that we need neutron sources, and these are the ones. And we also have to have a simpler representation, yet a triplo representation. So we can go on and packing, and we find that the idea here is one of marginal accretion. So we build up margins, and we have neutrons excess to be able to smoothen out the contours of this. And here we have another from zinc to krypton, and we have it in another version. And we see that now we can see the fourth period here in a simpler way. We can see that we come to square structures, and they are flat, so to say, surface structures. And we see the anticipated fifth period, sixth period, and seventh period here. We also see the difference to the standard model, which has these gaps and these extra rows for the actinides and lanthanides. We also see that all are space filling by the construction. Here I show you one spacing. And if we get a square quadratic, also fill space very nicely. So we go on from krypton to rhodium. This is the period coming. You should see. And we come to xenon. And xenon completes the fifth period. And here I make a little we have xenon completing the 5th period and starting up the 6th period. And 6th period, now we have the lanthanides starting here, you can see. And it comes to European, it's getting a bit more European. And from European to hafnium, lanthanides start node saturation and subshell and so forth and so on. So we have the kind of structure here that we should see. We can see that the margins are increasing. And we come to gold. Gold has a very symmetric structure. It's always this just marginal accretion. And we see the isotopes. That's the interesting thing, that we have the isotopes here. And some are stable and some are not, but they are all very well. And we have this one coming to the next one. Yeah, now we completed the 6th period, and it's rather interesting to see that we have all the kind of alpha channels and beta channels and so forth and so on. The beta channels are marked with an R. Now we shall have a time for this. This is the 7th period, and we see that it has a very nice kind of symmetry here, and that you can make various kind of space feelings of it with inverses and so forth and so on. And another thing to note here is that the alpha diameter, the diameter of a unit cells, as it were, which is a helium atom really, is femtometer scale. But a full atom diameter is 10,000 times larger. So this puts us in a dilemma. We have only made small blocks here, but how shall we go on to the big blocks? And that is the content of the next slide here, which shall come now, I think. Yeah, I still have 5 minutes. This was... It should come. Yeah, this is a kind of problematic structure, but now it surpassed us here. It's, yes, yes. We shall see that in the I don't go back to that slide because that took too much time to materialize. We can only say that it filled the plane with about 10,000 fold of itself. So we come to place here, and in order to make a full atom, it's done when it's equally high as wide. I think this is a tessellation of a plane in that case. And we move on and see that this is an ordinary structure here in many atoms that they too much time. Yeah, well, that's bad. we see that it takes 10,000 times of this to cover an atom diameter. And that is actually I have to go back. So it's awful when the slides are. But this, because that takes. Wait for this. Yeah, now it comes on. And hopefully it leaves. Yeah, now in the next. And now we have a bit slower time here. So we can see that actually this is how atoms are constructed. They come in sheets. Yes, I take it back to 259 then. Yes, why isn't it? Seems to have obstruct. Yeah. No, we shall see. It's hopeless to get in order here. It's getting blocked.
Sorry?
It's getting blocked, the kind of presentation. Anyhow, are you still hearing me? This is how a silicon atom is the kind of central nucleus and covalent electron bonds, but in reality it's a kind of such surface you see. You always see the atom surface like this. Now we shall see if we can come on. It's simply out of the question. It has been blocked, this so I don't really know what to. We shall see if I can come. Yes, here we have the kind of atom structure that you see. And you see that these are not holes, these are the plates of atoms. And these are holes. And so there is a difference. But there are big structures, the atom surfaces. But I'm sorry, I seem to have had irreparable problems here with my presentation. But no, okay, let's go on to start the last round, and hopefully we come to conclusion here. We have to make just 5 minutes addition for the problems here, because we are now in the seventh period, and we shall hope that it comes across thorium, only alpha decay channels. So in this, and now we have come to fermium, so now it will come rather soon, I think. Thorium. has been. Yes, and now we have come to Hassium and starting the last two organisms. So we can see that the rows are isotopes, and we can see the rising orders of, and always that kind of marginal accretion, creating what you can say ground unit surfaces, but to full atom plate, it has to be very wide. But now we should see. Yes, now we have come to organism. So this should be the goal, and that is the highest atom, and it's very symmetric. And you can say that is the complete atom, and it has isomers, of course, and it has continuations, so you can go on from unionensium, perhaps till the 8th period. That should be possible. Anyhow, I just come to an final. So, but now again, we have 100 million base pairs shall be crossed. Is it realistic? Well, we can see that there is a method. The Hilbert cube filling curves show it's possible, but by a solid line. And we can show that it's not impossible, because a chromosome has 248,956,222 base pairs packed in a structure with coils and everything that are just 6 micrometers wide. And this is still smaller. But how shall we get there for us? Well, we can really find a way of making the kind of packets here. If you start with this curve, it's a square wave up, and we reach an end, it just turns and goes down, and then it fills a tubular structure. And that can be rectangular here to fill spheroid wave structures. So this is just how we shall have the wave packets arranged so that you can really scan off the kind of structure. And we can say that also applies to the wave, because the wave has also one upgoing arm and one downgoing arm when it turns, and then it forms this kind of structure, which is just one line, because you really can't form this in one continuous line, but you have to form them up and down, so it were. And then they combined to what we can call wave packet, which will bend and fill their atom plates. And it takes 100 million of these to fill space, but it's not very much. It's much easier, you could say, than fill a chromosome, because a chromosome base pair is larger than this base pair, which is proton and neutron. So we can say that we have R3 times SO3 wave packets, which fill space, and as a unit, they remind very much of Clifford tree vectors, which is also a kind of cubic structure with a wave. I have to conclude, and this is Swedish for thank you for your attention. I did not think I exceeded time too much, but it was a lot of faults in the presentation. Thank you. Thank you.
Thank you, Eric, for your, as usual, nice presentation with really precious images that every year you show. I guess due to the size of the image, this is two heavy images that you are showing us. Maybe the computer takes more time to operate, I guess so. So may I now request all of you to have any question, comments, if you have any, please let us know. So you can directly ask question to Eric if you wish. Or you can, those who are on the YouTube can directly share their comments or questions. Then directly I can send it to him or I can email him if you wish. So I don't find any question here, not on the YouTube as well. Just one thing to note, just now I have seen that yesterday's the conference YouTube viewers is more than 1,000 now. So it's more than 1,000 people have already viewed yesterday's program. So it's really a great success, and I'm sure that today also we are getting almost similar kind of view that we'll able to come to know maybe at the end of the whole conference. Okay, it's a great news. So with that, once again, may I thanks Eric. And
Thank you.
as usual, little bit reorganization of the talk. May I now request Shubhra Bhattacharya. So Professor Fatukan, I can see that you are here, but maybe we can first, so maybe you can take some rest and then maybe we can start your next, if you wish.
Yes, sure.
Okay, so yeah, Dr. Shubhra Bhattacharya, may I now request Dr. Shubhra Bhattacharya to start your presentation. The title of her talk will be Revisiting the Dynamic Floridian Wormhole. Shubhra, could you please? Okay, so may I now request,
Yes, I am here. I think.
Yes, Eric is sharing his screen. So
Yes,
Eric,
yes.
could you please stop sharing the screen? You can see the stop sharing button.
Yes. Stop sharing.
Yeah, you can press there itself on the sharing button on the left. Yes, on the left, on the box. Yes, on that box.
Yes. Stop
You
sharing.
can, I can see in a Swedish language, not that one. That will end up the meeting. So some presentation. Obstula presentation. Yes, great. Thank you.
Yeah, so I should start presenting my screen.
Yes.
Den hakar upp sig. Presentationen.
Sorry, I'm not on the first slide. Okay, is my screen visible?
Yes, you have your screen and you're audible as well. So you will have 20 minutes. So please.
Okay. Thank you, Professor Odhikari, and thank you, Professor Trill, for such a nice talk. For myself, I'm Dr. Shubhra Bhattacharya, and I'll be talking about the dynamic Lorentzian wormholes. So the plan of my talk is, first, I will give a very brief introduction of wormholes. I'll first define what they are, and I'll be describing them, and then I will take you through a small journey of how they evolved mathematically. This will be followed by the precise mathematical description of the problem at hand, and I will be describing the various solutions and how those solutions, in the fourth part here, I describe how the solutions will be significant or important from the point of view of the wormholes, which we are going to discuss today. This will be, excuse me, followed by the development of the matter-energy tensors, which are responsible for supporting the wormholes. And finally, shall end my talk with a small conclusion, with my concluding words. So first things are first, what is a wormhole? So wormholes are structures in space-time which are characterized by a non-trivial topology. So wormholes are actually obtained as solutions of the Einstein's field equation, but they are mathematical reality, although they are still speculative in the sense that no wormholes have been really spotted in the universe, unlike their black hole counterpart. So the problem with wormholes is that they are characterized by highly warped structure in the space-time. As a result, the topological censorship conjecture prevents the sighting of such wormholes. Because such non-trivial topology, if they at all exist in the universe, would have a tendency to pinch off due to gravitational collapse. And once there is a gravitational collapse, the cosmic censorship conjecture comes into hold, and that will surround that gravitationally collapsed region in an event horizon. And event horizons are again impossible membranes or boundaries which does not allow signal from the outside world to enter. As a result, it is difficult to view a wormhole, but nonetheless, wormholes are mathematically true, and they are obtained as solutions of Einstein's field equation. And there is some romanticism associated with wormholes in the sense that they are conceived of shortcuts between distant regions of the universe and are ideal for building up structures like time machines. So, if I go through a journey of how wormholes were developed, the first mention of wormholes could be found in the literature of Ludwig von Flamm. He actually mentioned them as contributions of Einstein's GR soon after Einstein's general relativity was put forward in 1916. He mentioned them in his first paper in 1916. And then after that, it was Einstein and Rosen who in 1935 mentioned them as some bridges, or popularly known as the Einstein-Rosen bridges, which were like connection between two distant asymptotically flat spacetimes. Later on in 1955, it was Wheeler, Archibald Wheeler, who in his famous work on geometry dynamics actually laid down the foundation of such handles in space-time. And then in another couple of years, sorry, there is a printing error. It's 195, it should be 1957. Wisner and Wheeler coined the term wormhole, describing such highly warped spacetimes. And then there was, you could see a lull, after which there were sporadic works by Bronikov, and then Kodama in 1978 described the wormholes as King solutions, and Ellis in 1979 as the drain hole solutions, and later on Clement described them in high dimensional gravity. But the current paper, or the current work that I'm going to discuss with you, will be based on the 1988 seminal work by Morris and Thorne, who kind of brought forward a new description of wormholes, which in a way revolutionized the way we look at wormholes nowadays, and it can be associated with a renewed vigor and interest in wormhole science and wormhole mathematics. So we will be working with evolving wormhole geometries, which are in line with Morris-Thorne wormhole. But then Morris-Thorne proposed a static wormhole geometry, while we will be working on evolving wormhole geometry. So equation number 1, as given in the presentation, describes a space-time metric which can have a wormhole-like structure. Just to mention briefly, this function e to the power phi rt is called the redshift function, and it is associated with the identification of event horizon in space-time. And as I told you, event horizons are membranes which cover singularities, and these are impossible membranes. So since wormholes are associated with we want to build wormholes, or we want to acquire a wormhole with the aim of building a time machine, we do not want an event horizon. So this function, which is associated with the time coordinate, should be regular. And And this should not have any singularity in order to prevent the formation of an event horizon. The other function BR is again significant because this indicates the throat of a wormhole. Here the throat is the joint between the two space-times, and the point at which the two space-times are joined or linked should have a minimum surface area with asymptotic flare. And this function BR is called the shape function. And we assume that this geometry is supported by anisotropic matter stress energy tensors. And correspondingly, if we write the field equations, these are the four field equations. Now let me tell you how we shall plan to analyze this. Okay, so the conventional way of working with wormholes is to solve the Einstein's field equations. So in the Einstein's field equations, we have the geometry on one part and the matter stress energy tensor on the other part. Am I audible, or is there a problem with the connection?
No, you are still audible.
Oh, okay. Thank you. I just got scared. So in the Einstein's field equation, we have the geometry of the space-time connected with the matter stress energy tensor. And the conventional way is to have a known stress energy tensor, and with that known stress energy tensor, we solve the geometry of the space-time. And that is usually gives us all these problems with singularities. The other way is to fix a suitable geometry without a singularity or without an event horizon, and then solve the Einstein's field equation, which in turn will give us the matter stress energy tensor. But then this creates the problem of the resulting ensuing matter stress energy tensors are all exotic in nature, means certain type of matter stress energy tensor which we are not aware of or which is not physically possible. So there is a problem either way. We will, on the other hand, take a middle way where we do not fix the matter stress energy tensor or the geometry, but we try to solve both of them in a coupled manner. But at the same time, we're going to put constraints so that constraints on our function so that we do not get so that the geometry, the wormhole geometry is not violated, in the sense we do not get event horizons, or the wormhole throat condition is obeyed. When we try to do that, we arrive at these four field equations. And interestingly, we arrive at this equation number 5, which is actually a constraint, which does not usually arise in regular geometries. Okay, but since here we have taken the redshift function depending on both the temporal as well as the radial coordinate, we have obtained this fifth constraint equation. This fifth constraint equation has to be resolved first, and this will lead to several possibilities or outcomes. The first outcome, if you analyze equation number 5 very well, so since the left hand side is a 0, we must have either this dot A. Again, let me introduce you. A is the scale factor, which is just a scaling of the temporal coordinate or the time coordinate. So this A dot can be 0, or this phi r term can be 0, or we can have a situation where this shape function becomes equal to r. Now this now if A dot is equal to 0, then we actually arrive at a static wormhole geometry, which is not what we want to analyze. Now we are dealing with an evolving geometry, so we cannot have A dot equal to 0. So that is ruled out. That possibility is ruled out. The second possibility is if BR is equal to R. Now if BR is equal to R, then the constraint is obeyed. But then we actually get a geometry which is conformal to the FRW geometry, and which again is not going to give us a wormhole. So BR is equal to R is not something that we can adopt under the given geometry that under our assumed geometry which we want to study. The last condition is that the radial dependence of this phi term is that the phi function is radially independent of the radial coordinate. That is, del phi del r is equal to 0. This is the only condition probably we can assume. And if this is assumed, then the wormhole remains dynamic, and as well as the metric remains a wormhole. So we are going to do away with this radial dependence of this redshift function. Actually, this condition gives us one very strong result that wormhole geometries which are supported by anisotropic matter cannot have this radial coordinate dependence. So this is something we show through our work. Next is, if we return back to the field equations, this equation constraint number 5 is resolved. We are left with 2, 3, 4. And if we analyze 3 and 4 and put in the constraint of this function phi being independent of the radial coordinate, we arrive that 3 and 4, which gives the matter stress tensor, are related, can be fixed and related by this by a relation like this, where alpha is a function of the radial coordinate or can be considered to be a constant. So this is some extra advantage that we get due to the constraint. And since we have already fixed the matter stress energy tensor, these are the corresponding conservation equations which these rho, PR, and PT satisfies. And please understand, this PR and PT does not indicate partial derivative. Instead, these are terminologies that are used to describe the anisotropic state, the stresses along the lateral and transverse direction. So 6 and 7 are the matter conservation equations, which will later, together with the Einstein field equations, help us to determine the matter stresses. So using this relation, that is PR is related by this alpha term, alpha being a function of the radial coordinate or a constant with the transverse pressure, we arrive at this master equation number 8. So this master equation will help us get the solutions for this shape function as well as the radial, the scale factor E. Here note that this term H gives us the relative expansion of the universe, because this is the Hubble parameter and is given by A dot by A. So when we try to, we will solve equation number 8, and from 8 we get equations 9 and 10. So equation 9 will help us give the scale factor, whereas equation 10 will help us give the shape function B. And so there are several possibilities when we try to solve equation number 9. The first being the trivial solution, where we say that we are going to consider dynamic wormholes with zero tidal force. That is, there is the time component has only does not have any coefficients associated with it. And then the wormhole metric reduces takes this form of equation 11, and actually this can describe several type of cosmological scenarios. Since this our scale factor will have beta, which is a parameter dependence. So depending upon the various values that this beta takes up, we will have different cosmological scenarios. Like we can have, for beta greater than 0, expanding cosmology, which is given by the de Sitter line element. Or if beta is less than 0, we can have the anti-de Sitter space-time, or if beta is equal to 0, we can have a Milne universe. But this apart, this is the trivial solution that we talked about. There are other general solutions, and the most general solution will be given by equation number 12, and equation number 13 will give us another general solution, which in the limit, since C1 and C2 are arbitrary constants, these can be substituted, C2 can be substituted as 0 and C1 as 1, and this will give us the cosmologically relevant Einstein de Sitter universe, expanding universe. Now we have found out cosmologically relevant scale factors for our wormhole geometry. We try to determine the corresponding shape function that will give us geometry conformal to the wormhole. And this is the corresponding equation of the shape function. And we solve this to get our equation 14, where the function gr is related to the function alpha r, which decided the relation between the radial and the transverse component of the stress tensors. Now, since we have obtained our shape function as well as the scale factor, we can substitute this in our metric to obtain the final metric equation number 15. And this is a very significant equation that we get because this one solution has various possibilities, and the solution is very versatile in the sense that we can get a whole lot of solutions depending upon the choice of parameters that we want to take. So we have actually developed a method as well as have given a solution which encompasses several cosmological scenarios, and it also encompasses a tenable or a viable wormhole geometry. For example, we had this parameter beta, and this beta actually, if we look into the metric 15, can be interpreted as the curvature of the space-time. So we know that it is usually taken that we are living in a flat space-time for which beta will assume the value 0. If we are living in a closed space-time, then beta will assume the value +1, and for an open space-time, it will assume the value -1.
So Dr. Bhatt, we have 2 minutes more.
Okay, I will try to finish as fast as possible. So the wormhole throat is now described by this function g square r, and we will be able to obtain a static wormhole geometry in the limiting sense as well as the FRW line element. Now, in order to find out viable form of the shape function, we will put in different values for gr, and you see that we have obtained these 4 different shape functions which all conform to evolving wormhole geometry. So you see, we have determined the geometry of the space-time, and now once we have determined the geometry of the space-time, the values of this BR and AT that we have found will help us determine the matter stress energy tensor, depending upon which will be obtained through the conservation equations that I showed you before. And 20 and 21 gives us the matter stresses, the radial stress and the transverse stress, and this is the matter energy tensor given by 22, and all of these are obtained in terms of AT and GR. And next, we try to find out the null energy conditions that will be satisfied by these matter stress energy tensors, and these 2 equations gives us the corresponding null energy conditions, and we have numerically shown that there will be scenarios based on the choice of the parameters that we will have viable wormholes which will be supported by matter stress energy tensors that obey the null energy condition, which otherwise is not usual scenario in the literature. So in all these figures, we have shown different choices we have taken different solutions that we have obtained for our scale factor as well as the different wormhole geometries that we have obtained depending upon the shape function, and corresponding to viable parameter values, we see that all of these geometries will actually have which actually satisfy the null energy conditions. So these are the 3 figures, and hence to conclude, our work shows for the first time that the time-dependent evolving wormhole geometries will not have radially dependent time component. We have obtained wormhole solutions with only time-dependent 0-0 component metric tensor. We have actually described a general method of obtaining such solutions, and this can be applied to a whole lot of wormhole geometries. We have further discussed the different viable wormhole solutions. That is, we have given examples, and we have also shown that such geometries can survive with matter stress energy tensor satisfying the null energy condition. And all these solutions are cosmological in nature and can exist in different cosmological scenarios that we have successfully obtained, that we successfully know have existed and exists in universe. So, and there is also a physical interpretation of our parameter beta, which indicates the curvature of the universe. So this work has many facets and describes the wormhole, that is, the evolving wormholes in totality. That's all. Thank you.
Thank you, Dr. Bhattacharya, for your nice presentation. Any question, comments from the audience, if you have? Those who are on YouTube can also post questions or comments on the chat box. Okay, so no question yet. So many comments thanking you to the authors, to the speakers. Okay, so if no more question, then let's thanks once again to Dr. Shubhra Bhattacharya for a nice presentation. Now may I switch to Dr. Fatukon. So are you here, present there? Professor Fatukon, are you there?
Yes, I'm there.
Are you ready, or we'll go?
Go for the next one.
Okay, so maybe then we can directly.
I'll take after the next one, yes.
Okay, okay, great.
Yes.
Then may I request Professor Gulsum Uka from Turkey. Professor Uka, are you there?
Yes, I'm here. I can present. Thank you.
Thank you.
1 minute. Okay.
At the bottom, can you see an arrow box? Yes, fine, great. It's done. Yeah.
I think it's okay now.
Yes, fine. It's full screen. Yeah.
Okay. I am Gülsüm Yüca. I am in Turkey, in Aksaray University. In Faculty of Science, Department of Mathematics. First of all, I would like to thank the organizing committee and the scientific committee for giving us this opportunity to present online, during these pandemic days. You are in India, I'm in Turkey, and we can meet. I think that's so good. Thank you for this, first of all. My study entitled with hyperdual matrices in Euclidean and Lorentzian spaces. In this study, we define a dual transformation between hyperdual orthogonal matrices and hyperdual semi-orthogonal matrices. We show that the dual transformation leave invariant the axis in both spaces. We have extended this dual transformation study. Actually, it's defined first in Dohi's paper. We use this with hyperdual matrices. I haven't prepared Beamer mode because I have many definitions and theorems, so I did this with the paper. So sorry for this. Can you hear me?
Yes, we can hear you, and
okay. Okay, thank you. So I can skip the introduction part, I think. I just want to say that hyperdual numbers are the extension of dual numbers. First of all, in rigid body kinematics, we use dual numbers because we use this for the rotation and the translation. Hyperdual numbers, their purpose is to enable a more direct computation of second-order derivatives. Hyperdual numbers are introduced by Fique and Alonso with the aim of demonstrating the advantage of hyperdual numbers in second-order numerical differentiation. And then Cohen and Shoham expressed the hyperdual number in terms of two dual numbers. Yes, here the basic concepts. First of all, I want to give the definition of dual number because we use dual numbers to define hyperdual numbers. A and A star are real numbers. A square equals to 0 here, epsilon square. The combination of A hat, I use A hat for the dual number, A tilde for the hyperdual number. Here we can say that A hat equals to A plus epsilon A star. It's called dual number. Here epsilon is the dual unit. Why it's okay? Yes, the third paper. Yes, the set of dual numbers is here. Can you see my cursor, the pointer?
Yes, we can see.
Okay, thank you. This set of D module is here. The set of dual vectors. We can show that A hat with an arrow. And then we can now define hyperdual numbers here. We observe the properties of dual numbers of order 2, briefly called hyperdual numbers. A hyperdual number A tilde is determined by two distinct non-real components with the properties epsilon 1 square, epsilon 2 square. They are all equal to 0. Here we denote A tilde with the hyperdual number. Here is the set of hyperdual number. A tilde is the element of hyperdual set. Actually, we can define a hyperdual number with two dual numbers. I said before with the A hat, I present the dual number. So A0 hat and A1 hat, they are all dual numbers, and we can show here the second presentation of hyperdual number set. We can show this. The addition and the multiplication in hyperdual numbers defined by here and here. Okay, here I want to skip all these and I want to define hyperdual matrices, which is the main focus of my study. Rigid body transformations is studied on the Lie group SO tilde 3 consisting of 3 times 3 hyperdual matrices. They satisfy A transpose, A tilde transpose multiply with A tilde. Then we have identity matrix and the determinant of this matrix is equals to 1, which is rotation, you know, the element of SO3. But here A tilde is a hyperdual matrix, so these are the elements of SO tilde 3. Here is the set of this. If the hyperdual orthogonal matrix A tilde satisfies the property, this one, the spatial orthogonal matrix, we call this, and we denote with SO tilde 3. And hence, the Lie algebras along with the bracket operation over matrices is obtained with this, which is consists of hyperdual skew-symmetric matrices. Why we use skew-symmetric matrices? Because in this study we use axes. Since we use hyperdual numbers and hyperdual sets, then our axis is dual lines. And we define this axis with the skew-symmetric matrices because there is a correspondence between this the direction vector of these lines with the skew symmetric matrices. That's why we use this. We denote with S tilde. Here is the skew symmetric matrix. We use this in order to show the dual transformations leave invariant in both spaces, the dual lines, the axis. R tilde is the matrix which through hyperdual angle theta tilde and the non-pure hyperdual unit axis S tilde. We can show this with this. We will use this matrix R tilde in the following. And also, since we study in Lorentzian space, we need to give some definitions through these concepts. First of all, I need to say that in Lorentzian metric we use in the study, the last element has the minus, and the sign matrix here, the last element is -1. We can skip all this. I will speed up. After that, I will give the definition of dual transformation. What is dual transformation in my study? It's a transformation that we take orthogonal matrices, which are elements of SON. Then, under this dual transformation, we obtain semi-orthogonal matrices in Lorentzian space. Actually, it was good for us in our first study when we use real numbers. We showed that in both spaces we have the same axis. So it was interesting for us. Then we use dual numbers, and this is the first study of us that we use hyperdual numbers. This is the first time we use it. Here is the dual transformation. This dual transformation works with this. If we have an orthogonal matrix, then we block this with just like here. B is the square matrix, and the A and N is the last element. We need this last element because in our formula here, you can see in the denominator, A and N is here. So we need a hypothesis. Hypothesis is A and N must be non-zero because here. Then if we use this dual transformation, we have semi-orthogonal matrices. This is called dual transformation because if we take semi-orthogonal matrices in Lorentzian space, then under the dual transformation, we obtain orthogonal matrices. So we go there and go back to here. I think that's why this is dual transformation. Hyperdual matrices and dual transformations is the main part of this study. We use these matrices again. This is hyperdual orthogonal, and this one is hyperdual semi-orthogonal matrices set. After using this, actually we need to put a hypothesis. The real part of this hyperdual number must be non-zero, and here also must be non-zero because I said before this comes to the denominator of this part. Then if we take orthogonal matrices with written the elements are hyperdual numbers, then we obtain in the Lorentzian space semi-orthogonal matrix. We can show this and we can check with this. Yes, it is semi-orthogonal matrices. And then here I show that we checked, and yes, it equals to sign matrix here. Okay, I will skip these. Here I show that the axis, the dual lines of hyperdual matrices are the same in both spaces. We can show that the axis of this in 2.2 here, the axis of this was S tilde, This is in Euclidean space, and here FR we denote with B tilde. B tilde is the semi-orthogonal matrix. We obtain this by using R tilde under the dual transformation. We acquire this, and we check that if we multiply with S and R, we obtain S because it leaves invariant the axis, this axis. And if we multiply B with the same S, then we obtain the same S again. With an example, we showed that here a hyperdual orthogonal matrix. We take this, and the corresponding skew symmetric matrix is S tilde. This is here. If we multiply this, then we can check that this is the axis left invariant by the dual transformation, and B is the matrix semi-orthogonal with the elements hyperdual numbers, and if we multiply this, then we have the same axis. Actually, it was interesting. We did this also in hyperdual numbers. Because we did this with real numbers, after that dual numbers, and then in Galilean geometry, in Galilean spaces, we try to study. And the last one was the quaternions. We are studying on this, and I don't know what will happen in the next time. This is the first time with studying with hyperdual numbers. So thank you so much for listening.
Thank you, Professor Uka, for your nice presentation. Any question or comments from anybody on YouTube? Maybe if you have any question on the YouTube, you can also post the question. I can share it with her. Okay.
Thank you.
Yes. So
Thank you so much.
Yes, getting compliments from audiences. On the YouTube also, I'm getting some comments. Thank you very much. Okay.
Thank you.
There is no other
Thank
question.
you so much. Thank you for the opportunity to present online. Thank you.
Okay, then.
I think I'm the only Turkish person.
Yes.
This is the first time for me.
Yeah, in our conference, we did have Turkish professors joined here. Okay,
thank you.
We'll talk later on. Okay, thank you very much. Okay, now may I now request Professor Fatukon to please start your presentation. The title of his talk will be Mathematical Modeling of Elliptic Drug Addiction and its Control Among Students of Tertiary Institutes. Okay, so Professor Fatukon, could you please? We cannot hear you, Professor. Please unmute yourself. Professor Fatukon, please unmute yourself.
Yeah, I've done that now.
Yes.
Are you hearing me now?
Yes, yes, perfect.
Okay. I just want to I want to change device so that it can be clearer, I can present better. Is it good evening, everybody?
Yes, good evening all.
I'm glad to be, yeah. I'm like I said, I'm changing my device so that I can. Yeah. It's not moving. Okay. Where is it? Yes, sir. Just a minute, please.
Yes, please take your time.
Okay. All right. Good. Okay. I think it's better now.
So some echo is going on. You need to mute one machine.
No, I will off it.
Yeah, now it's fine.
Can you hear me?
Yes, now we can hear you. Yeah.
Clear enough? I need to use the headphone.
Yes, it's clear. It's little bit echoing. It's little bit echoing. Could you please talk something? Yes.
The other system. Yes, I'm not on the other system.
Okay, it's fine now. Yes, please carry on.
Is it clearer now?
Yes, clear. Yeah.
It's okay. Thank you.
So I can't hear you.
So once again, good afternoon, everybody. Are you hearing me?
Yes, now I can hear you. Yeah, please carry on.
Okay. So like I said, I'm sorry for a little delay. So I'll be running through the slides in the next, I have about 30 slides to go through very briefly in the next few minutes. So let me quickly do the sharing.
Can you see an arrow within a box at the bottom?
Hello?
Yes. Yeah, now it's coming. Great. Yes, we can see it.
Okay.
I guess your internet connection has some problem, issue.
Sorry, hello?
Yes, yeah.
Okay. Sorry, there was a distraction from the call. Or you can see my slides, right?
Yes, yes, I can see. No, not yet.
A mathematical.
I can see your screen. Yes, now
Can
it's
you
clear.
see?
Yes, now it's visible. Yeah.
Okay, thank you. Okay, thank you. Now, I'll be talking on mathematical modeling of illicit drug addiction and its control among tertiary institution students. Well, for a start, this model is to be applied within Nigeria. However, we know it's a global phenomenon and a problem everywhere. Now, it's a global challenge that we need to look into. I want to see how we can apply mathematics to solve this challenge. And that is the idea we have because we have issues with the Nigeria system. And as a result, we can see that a lot of things, insecurity here and there, is caused by drug addiction and drug abuse. And let's form the motivation for this research work. The goal is to formulate a mathematical model for the prevalence of use of illicit drugs and how to control this spread. Today, I'll be talking about this, how it affects our institutions of higher learning. And like I said earlier, we want also to see how this affects our nation.
Sir, your slide is not.
You are not seeing my slide?
No, sir.
Okay, let me share it again. Let me just share a window then. How about this? Is it clearer now?
Yes, it's coming. Yeah, please,
Yeah.
please make it a full screen. Yes, please make it a full screen maybe.
Okay. Okay, I'll do that.
Not Zoom, but it's not a full screen. It's
No, I'll do that, don't worry.
okay.
Is it fine?
Not yet.
Oh, not yet?
No, it's not showing the full screen, but it's showing the Zoom version of it. It's zoomed.
Oh,
So could
okay.
you please go to press F5? Could you please press F5?
F5. I think I'm on full screen. Okay, let me
Okay, please
just a
continue.
minute.
Yeah.
I'm coming. Let me reshare. I thought the entire screen. How about this?
Yes, please carry on. Yeah.
Is it fine like this?
Yes, yes. Yes,
Yeah.
Okay.
it's fine.
It is clear.
Okay. Okay, thank you. So a question that we need to ask ourselves is our world safer with drug abuse and the legalization of it in some countries and societies? I think you will agree with me that the answer is a capital no. And that is the reason for this research work. Although it is still ongoing, it's not yet conclusive. We're looking towards expansion to other countries and continents because we need a safer world to live in and for the next generation. And I think this is where mathematics can affect our society positively. There are many adverse effects of drug addiction. I'll just pick 2 or 3 that is prevalent in our universities in Nigeria. The first one is alcohol. People may not know that alcohol has a long-lasting adverse effects on humans. In fact, it's the one that affects almost every part of the human system, starting from the brain, the lungs, the liver, the pancreas, the intestines, the eyes, the mouth, the throat, the heart, the stomach, even the muscles and the bones. Cocaine is also a common drug that students use in our higher institutions. It's also very wide, having negative effects on almost every part of the human body. Then the most common one among students of higher institutions in Nigeria and in Africa in particular is marijuana. That's what we call cannabis. Cannabis. They take it in different forms and it affects almost every part of the human body, the brain, the lungs, the reproductive systems. the bones, the eyes, the mouth, everywhere, even the blood vessels. And most interestingly, it affects the immune system. And that is where, that is why when we have a pandemic like the COVID-19, it thrives more where people legalize the use of cannabis or marijuana, and where some people have some maybe some diseases, and they are using some drugs that are based on cannabis or marijuana. It breaks them down so fast because the immune system is already compromised. In the higher institutions in Nigeria, I'm showing to you some picture that may not look so nice. This is what we see from youngsters who are in the higher institutions. It does not have respect for age or gender or even religion. You can see these pictures I'm portraying, and it is really terrible. And we must look for a solution. In 2017, a research was conducted. You may not see this picture very well, but it shows almost every part of our nation has some prevalence in one way or the other. The key here shows the prevalence between 1 to 10% for some of these whitish states. We have 37 states in Nigeria, 36 plus 1, the capital city, and everywhere there is a prevalence in one level or the other. And maybe I need to tell us here, maybe you have been hearing about Nigeria, and you hear about some insecurity problems. Where we have most of the insecurities in the Northeast, and that is where you have the highest prevalence of drug abuse as of 2017. And that shows us that if we want a peaceful state to live in, a peaceful world to live in, we must do something about the narcotics and the use of illicit drugs, and particularly when it's gaining ground among our students of higher institutions. Now, the mathematical and computational models for addiction is divided into four portions. We have to start off the neuropsychology, that's the ongoing nervous system activity, to the cognition, which has to do with the ability for them to study, to recognize, and then to build their brains, and then the conduct, that's the behavior. How does it affect the behavior? And the goal will be to have a recovery. What the research is all about, that was about the aim, is to develop a mathematical model for illicit drug use and addiction among tertiary institution students. That includes important processes of drug addiction, the progression, the detection, and the optimal control mechanism. Because if we just talk about it, there must be some control measures. And we want to build this into the model that we are formulating. How do we achieve this? Is to develop a mathematical model using the simple SEIR, that is susceptible, exposed, infected, and the recovery. The recovery may be either death or recovered. So, and then we use the simple one, SIR, just the susceptible, infected, and the recovery. These are epidemiological models, and we are blending them together to form a simple model that will take care of the higher institution scenario. Many people have tried to develop some models, but they have not been able to capture the most important strata of the society that promotes this evil more than any other strata. And you will agree with me, all over the world over, it is the adolescents and the young adults that are much more involved in this drug addiction, and it's having effect. You talk of religious fanaticism today. You cannot just do it because of ideology. You must use something to keep you doing that bad thing, because your system will be beyond your control. And so we want to see how we can formulate the model, get the underlying assumptions, and also implement this model. For the research study area, we are just going to take 3 geopolitical zones in Nigeria: the North Central, the Northwest, and the Southwest, because the other 3 will mimic what we have in this. The picture I'm showing you is a map of Nigeria, and then where we have picked the states to use for this research. Now the methods. That's the model formulation. Like I told you before, we are using a combination of SEIR and SIR, and I have the parameters that we are making use here for the mathematical model, for modeling the prevalence, the spread, and also the control. In this model, that's equation 1, we have N of T, which is discussing the homogeneous population at time T. And then we have the S of T, which is the susceptible class. Then we have that's the detected class for counseling. And then we have the E of T. We have the innocent class. We have the experimental class. We have the lightly drug users class, moderately drug users class. These are different classes that could be infected in the process. And then we have deeply or heavily drug users class. We have the treatment class. We have the immune class, that is those who have recovered and removed from drug addiction. And then we have the damaged class, mentally or physically affected class. Then we have the incarceration class. Those who, because of their, maybe they were detected and they refused to, maybe in the course of getting involved, they get involved into crime and they were detected. Another decision will expel them, or the security agencies will take them to correctional centers. So we have this model all encompassing. This is quite different from all other models we've seen touching drug addiction. And to formulate this model, we have the assumption, we take death rate, because we assume that the death rate is not equal to recruitment rate. Then recruited individuals are assumed to be all susceptible. That is, everybody in that group may be susceptible. And we have all those conditions there now. We made a compartmental representation of the model. And what does that mean? This is the schematic diagram of the model. It is both for illicit drug addiction, substance abuse spread, and also detection. And we also think of the control. What should be the control? This model, you can see, has the parameter pi, talking of the susceptible. That's from the entire population. As the student is recruited into the university, we see this. And then we also have mu, the ones that are not involved in the drug, they are innocent, and we want to seclude them from being involved. And then we have neta for the exposed. Again, among the exposed, there could be some who are innocent, who are morally okay. Maybe they are coming from a well-disciplined home. So we remove them also from that system. And from this exposed, we look at 5 different scenarios. We look at the first class that I've explained earlier. If you look at the description of this, I explained that I1, that's the experimental class. We have the innocent class, the experimental class, the lightly drug users class, moderately drug users class, and deeply or heavily drug users class. How do we determine these people? I think that should be a question to ask. Yes, we are going to use questionnaire and interviews at the point of entry into the university to determine the situation of each of these people. So we look at this, and when we look at all this, we see the affected and then the parameter that is controlling it. Among these, the innocent one, if they are well taken care of and separated, they will end up becoming recovered because they are not they have not been recruited into drug addiction. But from I1, I2, I3, and I4, these 4 classes have been recruited depending on their stages. Now, all of them will be subjected to treatment. And when they are subject to treatment, at the treatment level, that is where the control comes in. At the treatment level, we have the control coming in. We'll see the mathematics of all this as we make progress in this presentation. So, but this is the schematic diagram. It's like the flow chart that tells us what actually we want to do. And this will go a long way to make this model a very successful model. Now, we can see the description of each of these variables. The N of T, I said before, is the total population that comes in from the institution we are looking at. Then we take the susceptible class, the innocent stage, the experimental class, lightly drug users class, moderately drug users class, and deeply or heavily drug users class, then the detected class. This detected class, that is at the point of counseling, for counseling, at the point of interaction. Then we have the treatment class. From there, we have the immune class, those who have yielded to treatment, yielded to the counseling, and they are able to recover or removed from drug addiction. However, even in the midst of that, like I showed to us in the schematic diagram, there will be some set of people who will not be recoverable. They have gone too far, or they made up their mind maybe because of the family background or whatever they see around them, and they are not able to be recovered. Those ones will be in this compartment, and that will be a major issue for the society. They are the damaged class, and then we have the incarcerated class. Now, the model equations. We're going to use, like I said, the SEIR and the SIR combined together. And that gives us equation 2 of the model using the differential equation. We describe the progress of the drug addiction and control. Equation 2 is this, the rate of change that is susceptible with time. And that gives us the parameters that we have as explained earlier. And then the second equation that talks about the exposed. And for the exposed, all the I1, I2, I3, I4, we see the parameter, the rate of change in the meter. Maybe I quickly take you back. You see the rate of change, the omega, the theta, the sigma, and the tau. So they are the one that controls these rates of changes. So you have them here. We have alpha 1, alpha 2, alpha 3, also inclusive. Then the infected, that is those already there. So we have the 1, the 2, the I2, the I3, and it continues up to the last equation. So we have a very big model having 12 equations, and solving these equations will take us to, we didn't complete it. Will take us to the equilibrium stage, and then let me see the equilibrium stage, and then we'll be able to implement with data. Just permit me to quickly run through the control function that we are using. The control functions that we are using are as follows. We are using A of t, B of t. A of t is to reduce the impact of peer influence, and beta of t is to reduce the effect of the social influence. And then we have them in that order, and that will help us to achieve our goal. And once we achieve that goal, then we'll be able to, at the point of counseling, they will be counseled, and then we'll have a better society. That is our desire. And that is what this research is all about. Like I told you before, it's an ongoing work, and I want to believe in the next MSAST IBC conference, we'll be able to present the results. We pray that that time we'll have a physical meeting, and then we'll be able to present the full result. But let me quickly present to you the few things that we have under that. I'll quickly make a presentation of that now, and then we can make progress. Yeah, just a minute. Yes. Okay. So let me quickly present that page. Are you seeing my new screen?
Yes, we can see it.
Okay. Now, can you see proposed control?
Yes.
Okay, thank you. Now, these are the new things we are including that we don't have in any other model existing before now, that the rate of to reduce the impact of peer influence, we bring in the A of T among tertiary institution students, then we bring in B of T with respect to time to reduce the effect of social influence among the tertiary institution students, and then the effort on identifying illicit drug users. This is very, very germane because ordinarily an illicit drug user will not want to show up, but we want to use all means at the point of registration, at the point of, we go to maybe house of residencies, we give incentives to make sure that we're able to identify the drug user, because the approach is everybody will have a bit and a taste of it, but we want to see those who are really involved. And then we also have the measure, the control measure. This is the control measure, D of T. And we bring it into the 4, that is to measure the control or to stop the illicit drug addiction. That is by enlightenment and awareness, telling the people the cause and the effect. And then we have the value influence. The value influence. The value influence will be, maybe we'll go through some of their religious groups to tell them, let them know the value of what they are doing. And also, we also go through the parental influence. All this will help us in the control. After the detection, we put all this into the control. And then for the analysis, we have seen the model. We are going to go through the positivity, that boundedness, and region feasibility. This is pure mathematics. We look at the boundedness of the model, the space at which we are working. Of course, we are using the rectangular space, the XY space, that we are still in that space, but then we may need to move sometimes to the subordinate space because of the differential equations that are involved. Then we do the positivity of the solution. Every differential equation, we want to be sure that there is a solution. We go to the uniqueness and existence of solution for all these differential equations we are using. We have gone far in some of them. We are going to expand. Then we move to the equilibrium state. And we check the stability analysis. We look at the local stability analysis and the global analysis. We also check the liponov and the optimal control and the cost effectiveness, particularly of the control. This will take a lot on the primary data that we intend to get from the universities we have scheduled. But this won't take time. We'll use Google Form, and we also have research associates in these universities to assist us in getting the interview done and getting the result. Now, the bifurcation analysis will be done and the sensitivity analysis will be done to establish the validity of our model. And with this, we'll look at, we now come to the basic reproduction number and then the numerical solution. For the numerical solution, we're going to use existing methods that we have derived in numerical solution, and we're also going to use some software. We use the MATLAB and we use Maple to be able to achieve our goal. If this is done, we believe we'll be able to get a solution to our world. And I want to believe that our success in Nigeria will be able to expand to other countries of the world, particularly where drug abuse is more prevalent even than Nigeria's situation. Thank you very much.
Thank you, Professor Fatukon, for your nice, very relevant topic with a lot of actions, and we are hoping our best to see you next year in Kolkata when we are going to organize this conference in a physical mode as usual. So it's a time for question and answer. So any question, any comments, if you have, kindly put it on the chat box, or if you wish, you can directly ask this question to the speaker itself if you are on an online mode, or if you're on YouTube, you can directly write the question to the chat box. I can share it with the speaker. So I can see in the chat box few comments like nice presentation and all. In the YouTube also, thank you and all. Okay, so I don't see really any serious questions that could be asked to you. Okay, if not, then let's thanks once again the speaker, Professor Fatukon, for his nice lecture. Thank you, and hope to see you next year in a physical mode.
Thank you. Thank you.
Yes. So now we will directly switch to a paper presentation one by Chandan Goswami and Pinaki Sarkar. The title of the presentation will be a well-connected deterministic distribution strategy based on Chinese remainder theorem for even number of co-primes. So may I now request Chandan to please share your screen? Yes, he is sharing. And please start presenting. You have 10 minutes plus 2 minutes for question and answer. Please.
Am I audible?
Yes, you are perfectly audible.
Okay. So, hello everyone. I am Chandan Goswami, research scholar of Presidency University, Kolkata, India. First, I like to thank Secretary of IMBIC to giving me chance to present here. Such a wonderful platform. So my title of my presentation is a well-connected deterministic KP distribution strategy based on the Chinese remainder theorem for even numbers of co-primes. I work with one of my respected seniors, Dr. Pinaki Sarkar, this paper. So first I start my technical section. We all have known the term Alexa. This is Alexa. Alexa is a virtual assistant technology, and so via Alexa, anybody can operate their AC, refrigerator from anywhere via internet. So for that, IoT is a big role to contribute and they are present. They are to contribute and present the smart home and any smart object to operate via internet. So what is IoT? IoT is Internet of Things. So basically, in the earlier days, IoT or Internet of Things basically used for military purpose, for border security or anywhere, a country or any state. But nowadays, Internet is an increasingly important part of everyday life, people around the world. So for that, we all know that not only the internet is basically used for whole area, particularly manufacturing, telemedicine, and urban areas to develop the any country or any city. And all we know, every coin has two faces, and know the advancement of science and technology and their disadvantage of science and technology or the Internet of Things. So the IoT attack surface is any hacker or adversary attack the IoT device, and to operate the IoT device via any their object. So for that, we want to present a cryptographic viewpoint, how the IoT devices are secure or private with the help of mathematics. So first, I introduce the what is role of cryptography to the security purpose of IoT devices. The chief services of any cryptography protocol are confidentially, data integrity, authentication, and root repudiation all are known. But most cryptography mechanisms depend on basic components called keys, and the security of cryptography mechanisms depends on the security of keys contained therein. So secure management of keys describe the entire life cycle of keys. So for that, we want to try present here and IoT device, or we tally the IoT devices to the wireless sensor network. So each devices we can compare to an sensor nodes, and so we want to present here. So we want to present here the key management scheme of wireless sensor network. So wireless sensor network of key management scheme is three types: self-inference, pre-distribution, or trusted server. But pre-distribution is very good mechanism, and particularly pre-distribution has also three types: randomistic or probabilistic, deterministic or hybrid. And deterministic are three types: matrix based, polynomial based, and combinatorial based. But we know that the key distribution plays a vital role for the security of keys in any cryptography mechanism. So keys must be pre-distributed before deployment by uploading them to the devices, due to the lack of a secure mechanism for key distribution during the communication of any two nodes. So we want to describe the combinatorial design application in key distribution has been considered as a suitable method due to the low overhead in the shared key discovery phase between the two devices or two nodes. So basically, I want to tell about via mathematical background how cryptography protocols or any Internet of Things or any device can secure or secretly communicate between two nodes or two devices. And that is my target is the mathematical aspect of security and privacy of Internet of Things. So first, I introduce a well-known and popular theorem in number theory, which is Chinese remainder theorem. We all know that any are positive integer m1, m2, mr, just such that they are co-primes, that is GCD of mi and mj1 for I not equals to j, and c1, c2, crb any integers. Then the system of linear congruence, we all know the x congruent to c1 mod m1, x congruent to c2 mod m2, and x congruent to cr mod mr. has a simultaneous solution which is unique module low M1, M2, Mn. Consequently, we obtain an isomorphism via of ring homomorphism. If we get a ring isomorphism from ZP1 or ZP2, ZPn, the direct product of product of n many nodes to compare to and ZP1, P2, Pn rings. So the reverse direction is trivial. At any given x, we can compute x mod P1, x mod P2, and x mod P2. The proof of the theorem is obtained from the extended Euclidean algorithm and some standard computation. So via this, we construct a KP distribution scheme, and so that the scheme is more secure and for IoT devices or any wireless sensor network. So first I introduce a combinatorial design for CRT of even number of coprime. Basically in 2018, in the conference of ACM, Pinaki, Sarkar and et al. Introduced for n equals to 2. We introduce here for in general for even number of coprimes. Basically in 2018, the paper is published in the ACM conference for n equals to 2. We want to present here the even number of coprimes for CRT KPS, and we using this we construct a KP distribution scheme for CRT. So for that we present here the variety of the design is composed is n tuple and A1, A2, An. And A1 is basically belongs to ZP1, A2 basically ZP2, A3 ZP3, and An ZPn. So the total number of varieties is cardinality of ZP1, P2, Pn, and we all know the cardinality is P1, P2, Pn, product of P1, P2, Pn. And the block numbering of the design is delivered from the CRT isomorphism, where it's delivered from the CRT isomorphism. So from any x1, C1, C2, Cn, we can get from x1 congruent to C1 mod P1, x1 congruent to C2 mod P2, and mod Pn x1 congruent to Cn. So the number of blocks basically same is the number of varieties. So we introduce a balanced incomplete block design. So for that we construct the keyring of this keyring of this BIBT. So for that, consider any x in ZP1, P2, Pn with node IDs. If we take any node ID from the ring ZP1, P2, Pn and deliver from the CRT isomorphism, x congruent to x1, C2, Cn, and basically x congruent to C1, x congruent to C2, and x congruent to Cn. We now define the certain set of keys. So first we fixed the n by 2 numbers elements in any n tuple here, because as we know, as we already told that here n is an even number, so n by 2 is a positive integer. So I first fixed the last n by 2 numbers, and I vary the first n by 2 numbers varying. So basically each number is varying from ZP1, I1 is varying ZP1, I2 is varying from the set ZP2, and In by 2 is varying from ZPn by 2, and their complement. So basically first n by first case, we already define capital S of S1 is the first n by 2 elements varying, and last n by 2 elements is fixed. But SS complement, X1 complement is the first n by 2 elements is fixed and last n by 2 elements is varying. And similarly, we consider SS2 where the first element fixed and the position of n by 2 plus 2, one position element is fixed and continue this number as fixed, but others number is varying. Similarly, capital SS2 complement is this. So in this way, we construct a SN2. So n by 2 elements is fixed and L by 2 elements is varying over the field of corresponding ZPJ, where J is run over to n by 2 plus 1, and n minus 1. So here capital SS1, SS2, and Sn are created by cycling the variables I1, I2, and n minus 2. And the complement of each set is created by varying the other n by 2 position. So S is the union of Si. So In equals to 1 to n. And for X equals to eta by CRT, construct n by 2 nodes, carrying the node X is capital S Xi union Xi complement. So basically, we consider here the is variety of A1 to N present in blocks. In the total, there are P1, P2, Pn by 2, and so the now I count the total number of possible number of S1 and SS complement here. So already we told the every varying number is coming from the ZPJ. So J equals to 1 to N by 2, and then we find the is variety of is present block. So basically the value of K, and then we find the value or rank of the block. So now we introduce the connectivity. What is connectivity? Secure connectivity or simply connectivity of a network is defined as the probability that two nodes are connected by a secure link. So now we find that consider any two nodes, NXI or NYJ, where X is C1, C2, Cn, and Y D1, D2, Dn.
2 more minutes.
And okay, sir, and I and J varying from 1 to N by 2. We now prove that the rho equals to 1 for the CRT KPS of even prime scheme by demonstrating that even in the worst case scenario, here if any all coordinates are unequal for any two nodes X and Y, that means Ci not equal to Di, then we here already proved that the two nodes or two devices are connected, still connected with the connectivity probability 1. So for X, NXI are SX union SI dash, and for Y the keyring set SY and SY Z dash, for I and J varying from 1 to N by 2. So now keyring of NYJ contains this, and the keyring of NXI contains N, and note that NXI intersection NYZ not equals to 5 as the key C1, C2, Cj minus 1 and DJ to Dn by 2 plus J minus 1 and Cn by 2 plus J up to Cn is present in the both set. So are guarantee that minimum one shared key between the two nodes in the worst case scenario for any two devices or any two nodes. Consequently, rho equals to 1 for set KPS of even prime schemes. So this is my work, and these are the references. So, thank you.
Thank you, Chandan, for your nice presentation. So any question or comments from both YouTube as well as from Google Meet? If you have any direct questions from Google Meet, you can please directly ask to the speaker.
Yeah, I have a questions to Chandan. Hello.
Yes.
Chandan, in your lecture, you told that combinatorial design for CRT even number of primes.
Yes.
Is there any other design for CRT?
Yes, any one design exists. I already told that in 2018 in the same conference, Pinaki Sarkar et al. Already published for n equals to 2.
No, I just
what
talk about the combinatorial design. Is there any other design? Is there any other design for CRT even number of primes?
No, I not ever seen any design for CRT even number of primes.
Okay, if even number change in odd number, so what kind of changed in your system?
We already seen that for odd number of cases. We know that for any construction of the combinatorial design, the keyring order must be order of root n, where n is the number of node in the wireless sensor network. But here the preserve the property, but for n equals to even case, for n by 2 fixed and n by 2 varying. But in the odd case, if we tell particularly n equals to 3, so then the number of nodes and the number of keyring not preserved for 1 fixed 2 varying or 2 fixed 1 varying. For that case, not preserve the wireless sensor network and the construct of the combinatorial design. So for that, we not clearly describe or clearly terminate or any conclusion that for CRT KPS is constructible for any odd number of cases, n equals to odd cases.
Okay, I have one more question. That if you have a IoT device, then you just talk about the security purpose.
Yes.
Yes. So you have a IoT device. Then what kind of cryptographic attack would you like to check your IoT device?
Node capture attack, basically physical attack.
Yes, you have a IoT device. Then what would you like to implement a cryptographic attack on your device to check it is a good device or
good scheme?
Your
basically
secure.
I check graphically to compare the existing scheme that any resiliency parameter via any resiliency parameter such as failures or TS, so that our scheme is better than any other scheme. So via resiliency measurement, I see that our scheme is better.
Okay, so I think it's a time to close because we are running out of time. So if you have any further question, you can send email to Chandan Goswami. His email ID will be available in the proceedings. So I think we must stop here because it's a time for the next session to start. Yes, so with that, I thanks to all the speakers who have delivered nicely in this session. So I can see that the session chair for the next session, Professor Manikam, is already here. So welcome, Professor Manikam, and I hand it over to you to chair this session. Thank you.
All right. Are all the speakers there now?
Let's check. Yeah. So, Avtar Singh, are you here? Avtar? Avtar, are you here? Yeah, Avtar is here. Bapun Das, are you here?
Yes, sir.
Bapun Das, okay. Rupen Lama, are you here? Going there. Sanchita Pal. Sanchita, are you here? Okay, I can see her.
Yes, I'm here, sir.
Monidipa, are you here? Monidipa? She will join soon. Maybe Santosh Vishnath.
Yes.
Thank you. And Manoj Vandalai.
Yes, sir, I am here.
Okay, great. So all the speakers are here. So please, yeah, it's up to you.
Okay, so let's start. Good evening to most of you and good morning to people from US. The first talk is, the title is Reliability Analysis of CPP System, where working of standby unit depends on connecting unit by Mr. Avtar Singh from Punjab, India. Please go ahead, start your talk. Is Professor Avtar Singh there? Hello? Okay, good. Yeah, can you briefly introduce yourself? Okay, Department of Statistics. Okay, good. We don't hear you. No, you don't hear him.
Can you unmute yourself, please? Aptar? Okay. Then you are. Could you please just sign it out and come back again? Maybe your speaker might have some problem. Could you please just sign out and then come back again?
Or maybe we can switch the talks and then someone else can present. Okay.
Yes, let's see. Aptar, could you please share your screen? Aptar, can you hear us? Yeah, that's great. Can you hear us? We cannot hear you yet. Some noise is coming from your machine, from your end. Your microphone might have some problem. Still, we cannot hear you. So could you please try and maybe we can come back to you after maybe others. Yes, please. Okay. Yeah, maybe.
Okay, so let's go with the next speaker.
Yes.
Mr. Tapan Das from West Bengal, India. He will talk on fault-tolerant matrix basis for a graph or of a graph. Go ahead.
Please stop sharing. Aptar, could you please stop sharing your screen?
Am I audible, sir?
Yeah, you are audible. Let's Bapun to. Yeah, please.
Okay. Tapan Das. Yeah. Please go ahead. Good.
Good evening to everyone. I am Bapun Das.
Your video on if you have one, so we can see you presenting. That will be better.
Okay. There are some network issues, sir. I think so. It's better to stop my video.
Nice. Already. Go ahead.
I am Bapun Das, a scholar, Department of Mathematics, Balughat College. Today, my title of presentation is fault-tolerant metric basis of graph. First, we define the metric basis and we go through the fault-tolerant metric basis of graph. Here, we The concept of multi-dimension was first introduced by Slater in 1975, and actually this concept of multi-dimension is introduced to distinguish the different vertices in a graph. The researchers are interested to this problem for its application in different areas of science and technology, like network optimization, robot navigation, etc. Now we define some definition related to this concept. First, we define a graph G, and it denoted by G equal to V comma E. This is a simple connected graph. We denote the vertex set by V of G and S set by E of G. The distance between two vertices in this graph we defined as the length of the shortest path between U and V, and we denote it by dg of U comma V, or simply d of uv. We call a vertex U resolved to vertices U and V if the distances between d of ux is not equal to d of uy. Now we define a code of a vertex in a graph with respect to a set, with respect to an ordered set, actually, defined as a k tuple, and if we consider the set R as a set of vertices, for example, R1, R2, dot rk, then the tuple will be take form this type d of u r1, d of u r2, dot d du comma rn, and it denote it by c of u r. For example, for this graph, the code of v1 with respect to the set R, v1, v3 is 0 to v2 for on, so on and so forth. Now we define the resolving set. An ordered subset R of the vertex set is said to be a resolving set if for any two arbitrary vertices U and V, the code of U with respect to R not equal to the code of V with respect to R. In another word, we may say R is a resolving set if for two arbitrary vertices U and V, there exists at least one vertex W in R that resolve U and V. For example, here in this picture, V0 resolve the other vertices. The codes are 0 for V0, V1. For V0 code is 0, V1 for code V1 is on, and etc. For this graph also, it is a cycle of with 12 vertices. Here the resolving set V0 and V1. Here we are only there. It is that there are several resolving set for a graph, but we are mainly concentrated on the resolving set with minimum cardinality. With a special for a special reason, the resolving set with minimal cardinality is said to be a metric basis. This is our the main discussion, and the number, the minimum number is called the metric dimension. So here for the same graph, V0 will the minimum resolving set, and for this graph the metric dimension is 1. Next, for here we discuss some existing result on metric dimension for simple graphs. This result are discussed Chattand et al. A connected graph has metric dimension on if and only if it is a path graph, we have seen, and for a complete graph with n vertices, the metric dimension is n-1. Also, if G is a connected graph and its diameter is d, then the metric dimension is bounded by n-d. Also, for a cycle C with n vertices for n greater equal to 3, the metric dimension is 2. And last, this for a metric dimension of a square of cycle is 3 for n congruent to 0, 2, and 3 mod 4, and 4 if n congruent to 1 mod 4. we use this result in next slides also. Now we define the concept of fault tolerant dimension. A resolving set F is said to be a fault tolerant resolving set if F defines U is also a resolving set. That is, from a resolving set if we can delete or eliminate on vertex, but still the set will maintain the resolvability. Here, similar to metric dimension, the minimum cardinality resolving set, fault tolerant resolving set called fault tolerant metric basis, and the number is said to be fault tolerant metric dimension, and it will be denoted by beta dash of G. Here, this set, if here for this graph, V0 and V8 forms a fault tolerant metric basis, as well as a fault tolerant resolving set, as well as a fault tolerant metric basis. Here also some result for fault tolerant metric dimension. For a path, fault tolerant metric dimension is 2. For a connected, for a complete graph with n vertices, metric dimension is n. Also, Javed et al. Proved that for a cycle with n vertices, for n greater equal to 3, fault tolerant metric dimension is 3. Here some relation between metric dimension and fault tolerant metric dimension. Usually, it is easy to see that the fault tolerant metric dimension, that is beta of G greater equal to metric dimension beta of G plus 1. Also, Hernando and others determine the relation for any arbitrary graph G that fault tolerant metric dimension beta of G is bound by beta of G times 1 plus 2 times 5 to the power beta of G minus 1. Now we discuss our result on a fault tolerant resolving set and fault tolerant basis of a cycle, square of cyclic graph. The square of cycle graph we denote it by Cn2. It is this graph has the same vertex as a cycle Cn, and the two vertices we call adjacent if the distance between them is less than or equal to 2. For example, this is a cycle with vertices 8, and V0 or V2 is at distance 2, so they are adjacent by the line, and so on and so forth for the other vertices. Now, we define a lower bound for the fault tolerant metric dimension for square of cycle. Here it is for 4 if n congruent to 0, 2 and 3 mod 4, and 5 if n congruent to 1 mod 4. This is very easy to observe from the inequalities beta of G greater equal to beta of G plus 1, and the result we have previously seen that metric dimension of square of cycle is 3 for 3 for n congruent to 0 to mod 3, congruent to mod 4, and 4 if n congruent to 1 mod 4. So this is, now we discuss about its reverse inequality, that is beta square beta dash equal beta dash of Cn square less equal to 4 if n congruent to 0 mod 2 0 2 3 0 2 3 mod 4, and 5 if n congruent to 1 mod 4. We prove this upper bound by constructing a fault tolerant resolving set with cardinality 4 and a set resolving set with cardinality 5. And this is here the construction of the basis for n congruent to 2 and 3 mod 4. The set V0, V1, V2, V3 is a fault tolerant resolving set of Cn square, where the vertices are in cyclic order, as we previously seen in the picture of the cycle. Also, for n congruent to 0 mod 4, the set V0, V1, Vn by 2, Vn by 2 plus 1 is also a fault tolerant resolving set of Cn square, and these two sets are of cardinality 4. And for the n congruent to 1 mod 4, This set, that is V0, V1, V2, Vn plus 1 by 2, Vn plus 3 by 2 is also a Fulton resolving set. It forms a Fulton resolving set of Cn square. And these are the useful references. Thank you.
Any questions from anybody? Good. All right. If there are no questions, let's proceed to the next talk. Mr. Avtar Singh, are you ready to make presentation?
Yes, sir. Now I'm ready.
Okay, go ahead. Start.
Okay, sir. Thanks. Is this visible to all?
Yeah.
My presentation?
Yes.
Sorry for the inconvenience at first. To now, topic of my presentation is reliability analysis of CPP system, where working of standby units depends upon connecting unit. These are the contents of my presentation. These are introduction, notations, state transition diagram, transition probabilities with mean sojourn times, then mean time to system failure, then availability analysis, busy period analysis of repairment, expected number of repairs, particular cases, graphical representation. Now, coming to introduction, every production industry focus on the ancillary activities like steam and electricity generation, which in turn is a flexible and reliable power supply for the industry, and also plays important role in decreasing operating cost of the system. Various authors like Singh and Taneja in 2014, Nathani et al. In 2017 have worked on the cost effectiveness of on various aspects of the systems. Prasher and Taneja in 2007, Matthew et al. In 2010 have worked on the various type of redundant systems. Sharma and Kaur in 2016 have studied two unit standby system with one side by essential generator to increase functioning of the system. Rajesh and Prasher in 2018 have carried out the reliability analysis of 3-unit gas turbine power generation system with the first come first serve repair priority, but at some extent the system goes to down when the turbine fails. However, such situations cannot be overlooked in the production industry, where continuous supply of electricity is required for processing. Similar situation may exist in NFL when there is failure in power generating systems, and the only possibility is to buy electricity from outside sources. Keeping in view the above, the concept of breaker is introduced here. Present paper concentrate on the profit analysis of captive power plant of National Fertilizer Limited, Batinda, where the working of PSPCL supply line depends upon the breaker on turbine failures. The system consists of two steam turbine generators, STGs, PSPCL supply line, and breakers. The initial system works on full capacity on two STGs, and PSPCL supply line is kept as standby. On failure of any one of the STG, breaker interconnects the line to PSPCL, and for small amount of time, the system goes to halt state. But if breaker fails, the safety relays would cut off the load from the operating STG, leading to system failure. Also, if PSPCL supply line fails, the breaker operates successfully, then system goes to reduced capacity with one STG as working. Here, breaker cuts off the load with PSPCL to prevent reverse feeding of electricity to PSPCL supply line, which will damage the steam turbine generators. Various system effectiveness measures such as mean time to system failure, availability analysis, busy period of repairman, number of repairs, and profit analysis have been calculated numerically as well as graphically using semi-Markov processes and regenerative point techniques using the following assumptions. The assumptions for my model are: failure times are assumed to follow exponential distribution. Units work as good as new after every repair. Among two steam turbine generators, repair priority is given to recently failed units. In case of breaker failure, it is repaired immediately among all units. In case of failure of two STGs and PSPCL, repair priority is given to PSPCL. And these are the notations for my model. Lambda 1 is a constant failure rate of identical units which are STGs. Lambda 2 is constant failure of PSPCL. P is the probability that breaker will work. Q is that breaker will not work. Then beta is the rate with which breaker shifts the load to PSPCL. Then G1, capital G T is the CDF, and small gt is the PDF of repair time of steam turbine generators and PSPCL and breakers, etc. Now these are the symbols for my model. SI is the states of the symbol, state of system with number I. Then after that, ST is for steam turbine generators, P for PSPCL, BK is for breakers, and with these notations, we are coming to our model. In this model, the initial state is S naught, where both the steam turbine generators are working. PSPCL is at a standby, and breaker is also in standby. When any of these STGs would get failed, then and breaker operates successfully with probability P, then the breaker will shift the load to PSPCL, resulting to a small halt state. But when the breaker failed to shift the load with probability Q, then the system will goes to fail state. Here the repairman would come and operates the breaker. Then with that rate, the system will move to state S3, where as steam turbine generator and PSPCL are working. From this state, if only one pending steam turbine generator would get failed, then the system will move to state S4, where the system is running only on PSPCL. But when failure of PSPCL would get, then system will move to, but with failure of breaker, system would move to S5. But if breaker operates successfully on failure of PSPCL, system will move to state S6 with only one unit working, which is steam turbine generators. From this state, S4 initial state, system will move to either S3 or state S7, where all the units of the system would get failed. Now, from state S8, the system will move to only to back state S3 and state S9 with failure of steam turbine generators. From this is also our ninth state, from where system will move to state S10. And from this state, with the repair is going in steam turbine generators. From that, with the repair rate G1T, system will move to state S3 with where one STG is working and PSPCL supply line is working. Now, these are the transition probabilities for the system. The state transition diagram as shown in figure 1, the epochs of entry into the states S0, S1, S2, S3 up to S8 and 10 are regenerative points. So these are regenerative states. The state S2, S5 and S9 are failed state. These are transition probabilities. These are non-zero element PIJs. These non-zero elements are proving their sum of all probabilities equal to 1, and these are mean sojourn times mu I corresponding to regenerative state I. The unconditional mean time required by the system to transit from state Si to any regenerative state as J, when time is counted from the epoch of entrance in the state I is mathematically stated as this equation. Now coming to mean time to system failure, for determining the mean time to system failure of the system, the failed state of the system will be regarded as observing state. The mean time to system failure when the system starts from initial state S0 is given by this equation. Using the L-Hospital rule, we will get the value of T naught by putting the value of phi naught star S. Now coming to availability analysis at full capacity, when using the theory of regenerative processes, the availability at full capacity is given by this equation. Now busy period of repairman, using the theory of regenerative processes, busy period of repairman is given by this equation. Expected number of repairs are given by this equation. Now total profit incurred to the system in steady state is given by this equation, where C naught is the revenue per unit uptime of the system at full capacity, C1 revenue at reduced capacity, and C2 is the cost per unit time when repairman is busy, and C3 is the cost per repairs. The graphical representation is done by using the following particular cases where distribution of repair time has been taken as exponential, and the remaining distributions are same as in general case. So using these particular cases, we come to the graphical representation of MTSF versus failure rate of lambda 1, where lambda 1 is failure rate of first unit, means steam turbine generators. Here we see that as well as the failure rate of STG increases, mean time to system failure decreases. So these are the different lines for failure rate of other two STG working in the system. This is the graphical representation for profit versus cost revenue per unit uptime the system. As from this graph we can conclude that as well as the revenue per unit uptime of the system increases, then profit of the system also increases. These are the particular points. We can conclude that for lambda is equal to 0.0052, profit is positive or zero or negative according as our revenue per unit uptime of the system is greater than or equal to or less than 125.2. For lambda is equal to 0.052, profit is positive or zero or negative if our revenue per unit uptime is greater than or equal to or less than rupees 1109.8. And for lambda 1 is equal to 0.52, profit will be positive, zero or negative depending upon our revenue per unit uptime greater than equal to or less than rupees 5324. So these are references. Thank you.
Oh, well. Any questions for Mr. Alta? Any questions? No questions.
Can I stop sharing now?
Yeah, please.
Thanks to everyone.
Thank you. Let's move on to the next talk by Mr. Rupan Lama. The topic is fault-tolerant metric dimension of paths with tolerant level 2. Please go ahead, Rupan. Are you there? Rupan Lama.
Hello, sir. Am I audible?
Oh, good.
Am I audible, sir?
Yeah, you are. You are.
Okay, sir.
We hear you.
Okay, sir.
Mr. Singh, could you please disconnect your mic, mute your mic, yeah. Go ahead, Mr. Lama.
That screen visible, sir?
Yes, it is. Good.
Good evening to everyone. Warm regards from Balurghat, India. This is Rupen Lama from Balurghat College, and I'll be presenting the paper on fault-tolerant metric dimension of paths with tolerant level 2. First of all, we need to understand what is a graph. A graph is a mathematical representation of a network, and it describes the relationship between lines and points. The set of points will be called as nodes or vertices, which are interconnected by a set of lines called edges. Here, a VG is called the vertex set, and EG is your edge set. The distance between any two vertices, U and V, shall be denoted by DUV. The diameter of the graph is the maximum distance of any two vertices on the graph. When we move on, now we move on to the code and the resolving set. Supposingly we take a set S, an ordered set S consisting of M vertices, say S1 to Sm, which is a subset of G. Then code of V with respect to S is an M tuple of the distance from S1 to V, S2 to V, and so on to Sm to V. To understand this, let us take a path consisting of 4 vertices, say U1, U2, U3, and U4. If we take S as the set U1 and U3 consisting of 2 vertices, U1 and U3, then if we want to find the code of U1 with respect to S, then it's going to be 0, 2. Why 0, 2? It's because the distance of U1 to U1 is 0. The distance of U1, U3 with respect to U1 is 2. Similarly, we find the code of U2 with respect to S, which comes up as 1, 1. And the code of U3 with respect to S comes at 2, 0, and the code of U4 comes as, with respect to S, comes as 3, 1. Now the background of our problem. The study of the autonomous motion of a mobile robot is an interesting and fascinating and flourishing technology. But there are many problems or questions that one needs to pose. The first question is, where is the robot? The second question we can pose is, how does it move? And the third is, which map does it follow? Now, to study the question, where is the robot? This study is known as localization. By the word localization, we simply mean determinations of one position with respect to a reference frame. Now, a robot always wants to know at what direction or orientation or position it needs to follow so as to fulfill the desired task. Thus, localization is a central problem to navigate a robot in its moving space. There are many tools and techniques for studying the localization problem. Graph theory is one of them. Robot navigation space can be represented through graph G, where vertices are the points through which the robot travels, and the connections between these points represents your edges. Now, what we can do is that if we put all the signaling devices on all the nodes, then it will be very easy for us to locate the robot. But it is a very, very costly and tedious process. So to make it quite easy, what we can do is we can place an optimum number of signaling devices at the nodes. Now the question is, what is the minimum number of nodes that we can place on the signaling devices? So to study this, we take help of metric dimension, which is the study of finding the minimum number of nodes or signaling devices that we need to put on the nodes in using the concept of graph theory. This localization or navigation of a robot has been studied by Kuller et al. Now we come to the resolving set. Set R, which is a subset of G, is called a resolving set if code of V with respect to R is not equal to code of W with respect to R. If the codes are distinct, then we can say that R forms a resolving set. Our main aim is to determine a resolving set with minimum cardinality, and this minimum cardinality is called the metric dimension of G. In this figure, it is quite clear that even if we take 2 points, say V0 and V4, if we take V0 and V4, we can see that it is not, the system is not resolved, because we see that in V1 and V7, the codes are same. So hence the system is not being resolved either by V0 or V4. Hence the position at which we place the vertices is quite important. If we take a path, if we place our nodes or signaling devices at any of the endpoints, we see that, say we are placed here at V1, then we see that the codes with respect to all the vertices are distinct. Hence, the robot will be able to move freely without any interference. If we consider a cycle, if we move on to the figure that's given below, if we consider a cycle, in case of a cycle, only one placing the signaling devices only on one of the nodes or vertices is not going to suffice. So what we do is that we move on to figure C. In figure C, it is clear that if we place it at V2 and V3, the system is getting resolved. So there is no interference in this figure C. So now we move on to the background for fault-tolerant resolving set. From above, it is known that the localization of a robot navigation in space is designed by graph theory concept. Now these signaling devices, if you are placed on each element of the landmarks, now what will happen if one of the signaling devices fails? Then the whole system is going to crash. So to overcome this, what we do is we place one extra signaling devices on one of the nodes. Thus the finding the minimum number of landmarks where the signaling devices are placed in such a way that the fault in one signaling devices will not affect our system at all. So this is the fault-tolerant resolving system. To go to the mathematical definition, a resolving set R is said to be a fault-tolerant resolving set of G if we remove V from R, then still it is going to resolve the set G. As in the figure B, we have taken a cycle. There are 3 figures, A, B, and C. If you kindly look at figure B, if we take V2, V3, and V1, V2 and V3 is going to resolve the system, and one of the vertex, say here I have taken V1, will act like a backup. A resolving set F is said to be a resolving set with tolerant level 2 if here we remove 2 vertices, say U and V, from F. Then also it forms a resolving set. And the concept can be taken higher to K level. In K level, what happens is we, instead of removing 2 or 1, we remove K number of items. So resolving set K is said to be a fault-tolerant resolving set with tolerant level K if R minus S also forms a resolving set of G, and this S is any subset of Fk consisting of K elements. And in this figure, we have shown the fault-tolerant resolving set with tolerant level 2. Here we have taken V0 as V0, V1, V2, and V3. The system is going to be resolved even if there's a fault in any of the 2 signaling devices. Now some preliminary results on fault-tolerant resolving system set with tolerant level K. Here we consider a lemma. A set Fk is a fault-tolerant resolving set with tolerant level K if for any 2 vertices U and V, we have this set WUV such that W is an element of Fk and the distances from W to U and W of Vk are not equal, and this set consists of k plus 1 elements of Fk. The other lemma that we have proved is if Fk is a fault tolerant resolving set with tolerant level k, then Fk is greater than or equal to k plus 1. If there's an equality, then it holds, the equality will always hold good for path. Existing results for fault tolerant resolving set, Hernando, as our previous speaker had already mentioned, that the beta fault tolerant set for any tree T, beta dash G will be less than or equal to beta G into 1 plus 2 into 5 beta G minus 1. For a cycle, the fault tolerant resolving system is 3, and Shaha also determined the fault tolerant metric dimension for a cube of path for n greater than or equal to 7. Now, some important results. We take a theorem in which G be a simple connected graph. A set F is a resolving set with tolerant level 2 if and only if for every pair of distinct vertices in G is resolved by at least 3 elements of F. In the other theorem, we have proved that let G be a simple connected graph, then any resolving set with tolerant level 2 has cardinality at least 3. Now, what are our aims and results? Our main aim is to determine the two-level metric dimension of paths Pn. By an optimal resolving set with tolerant level 2, we mean a resolving set with tolerant level 2 that has minimum cardinality. Here we have also proved the theorem. For an n-vertex path Pn, any resolving set with tolerant level 2 has cardinality at least 4. The outlines of the proof I have given, but due to shortage of time, I won't be able to present the outlines of the proof. I move on to another result. For any integer n greater than or equal to 4, the two-level metric dimension of Pn is 4. Now we move on to the applications. What are the applications of the
You can take 2 more minutes. You can take 2 more minutes.
I'm done, sir. Fault tolerant in this system, the fault tolerant system, what we can do is the faulty sensors can be replaced, and it saves times as well as cost. And in a very high configured system where there are many computers, and there are chances of simultaneous failures and malfunctioning, this will help us to overcome this malfunctioning. It is also used in IT hubs, where we can reinstate important files and restore the system. These are some of the references that I have used to complete the paper. I would like to thank the organizing committee for giving me an opportunity to present my paper. Thank you very much.
Any questions from Mr. Lama? It's a very, very interesting result. I like it. Actually, I have done some work in this area. I have done robot navigation in unknown terrains.
Yes,
we have published few papers on this, but we didn't take distance into consideration at all.
Yes.
So I would like to get a copy of your paper. It's a very interesting result.
Yes, sir. Thank you so much, sir. It
You're
will be my delight to share some of my works with you. Thank you, sir.
Okay. Any other questions, anybody? All right. Good. Let's move on to the next talk then. Next talk is by Sanchita Paul on metric dimension of power of trees. Please go ahead.
Am I audible, sir?
Yes, you are now.
Okay. Is the screen visible?
Yep. Good.
Okay. Good evening, everyone. First of all, I would like to thank Professor Udikari, sir, and all other organizers and all the scientific members of this conference for giving me the opportunity to present the paper. The title of my paper is on metric dimension of power of trees. I am Sanchita Pal from Jadavpur University. So let's move to the introduction. The concept of metric dimension was introduced by Slater and Harary and Milter in 1975 and 1976. And since then, it has been widely investigated for many graph classes. Metric dimension is a parameter that has various applications in graph theory, pharmaceutical chemistry, robot navigation, combinatorial optimization, sensor networks, and many more real-life problems. So, for example, in a navigation problem, a robot moves from a node to node of a graph space. Now, the robot can locate itself by the presence of distinctly labeled landmark nodes in the graph space. Now, if the robot knows its distance to a sufficiently large set of landmarks, then its position on the graph can be uniquely determined. So here the first question comes that given a graph, what are the fewest number of landmarks needed and where they should be located so that the distances to the landmarks uniquely determine the robot positions on the graph. Now, a minimal set of landmarks which uniquely determine the robot positions is called the metric basis, and the minimum number of landmarks is called the metric dimension of a graph. Formally, we define the dissolving set of a connected graph to be a subset for which every pair of distinct vertices u and v, we can get their distances from all of the vertices of the set W to be distinct. That is, d of u comma wi is not equal to d of v comma wi. Now, these vertices of a dissolving set play an important role in uniquely identifying each pair of vertices by comparing their associated codes. By code, we mean the k tuple, where k is the number of elements of a dissolving set, and for every coordinate of the tuple is determined by the distances from each of the vertices of the dissolving set, as you can see here. Now, a dissolving set containing minimum number of vertices is called metric basis, and its cardinality is called metric dimension, and it is denoted by beta g. Now, next we move to the tree and its metric dimension. Now, this was solved by 1975 by Slater. He proved that beta of t, that is the metric dimension of a tree t, is exactly equal to the total number of pendants minus the total number of stem vertices. Now, let's move to this example for this discussion. So you can see here in this figure that there are 16 number of pendants here, as you can see. And whereas you can see the total number of stem vertices here is 6. Now, you may ask me, what is a stem vertex? A stem vertex is a vertex having its degree greater than equal to 3 and which possesses at least one of its branch as paths. Now, as you can see here that S1, S2, S3, S4, S5 and S6 are the vertices, are the stem vertices here. So the result follows from here. Now, next we move to the power of trees, which is our main focus. So in t to the power of r, that is the rth power of a tree, any two vertices are adjacent when their distance is at most r. Now, here in this picture, as you can see, we have drawn the adjacency of the vertex v in t square. So we have joined all the neighbors which are either at distance 1 or 2 from v. So in t to the power of r, distance between any two vertices are determined by this, that is d of uv by r and ceiling of that. Now, we move to some results on power of trees. So if we find that every resolving set of t to the power of r is also a resolving set of t. And an immediate conclusion we can draw from there that beta of t to the power of r is greater than equal to beta of t. Moreover, we able to see that if there is a vertex which is not a major stem but having its degree larger than greater than equal to 3, then there exist m-1 components of t containing major stems. So this is used in finding the upper bounds of the power of trees. Next, we move to the resolvability in square of tree, that is t square. Now, in this, we get that if there is an edge uv, then the vertex x can resolve this uv edge if the following conditions satisfied. Now, let's move to this example. So, if uv have its distance 1, then the vertices which are at even distance from either from u or from v can resolve UV. So as you can see in this figure that the red vertices are at distance 2 or 4 from U or V. So they can resolve this U and V. Now, what about this UV edge when its distance is 2? For these, we find that all the vertices except the vertex which is in the intermediate path of UV or that is coming from any branch from that, except them, all other vertices can resolve UV. So here also these red vertices can resolve this UV. Next, we find the criteria of resolvability in T cube, that is the cube of 3. So for these, we get that when the distance between UV is 1, then we find the vertices which are at distance 0 modulo 3 class, that is at 3m distance, multiple of 3 distance, those can resolve U and V, as you can see in this picture. And for when distance of UV is 2, then the vertices which are either in 0 or 2 mod 3 class, they can resolve UV. So in this case also, you can see this distance is 2, this is 3, this is 2, this is 3, this is 3. Okay. Now, what about the distance when the distance between UV is 3? In this case, we find some interesting thing that except the vertices which are, all the vertices which are left to U or which are left to V, that can also resolve UV. But some other vertices also can resolve UV if their distance from U and V, minimum distance from U and V is of 0 modulo 3 class. So as you can see, this vertex has distance from U as 3, that is 0 in modulo 3 class. Okay, so it resolves UV. Next, we find the resolvability of 2 non-adjacent vertices. And due to time constraint, I'm not going to details of this. So here also we have constructed this resolving vertices, and UV are possessing its distance 5. So this is certainly greater than 3. And these are the vertices, red vertices can resolve this UV. Next, we find the lower bound of a square of a tree, and that is actually equal to the total number of pendants minus the total number of stem vertices, which is actually equal to beta of t. So as you can see here that we have left only one leg apart from vertex choosing for finding out the dissolving set, and from all other legs we have picked up one vertex, as you can see in this figure. Now, next we find the lower bound of T cube, and now this is actually very interesting. This is actually becomes beta of T plus summation of mi minus L. So here mi is denotes the number of mid legs attached to a major stem Bi. Now, what is a mid leg? Mid leg is a 2-length leg attached to a major stem. Now, what is a major stem? Major stem is a stem having at least 2 legs. So as you can see here, V1 and V2 are 2 major stems. Now, from this lower bound criteria, we get that if there are more than one mid legs attached to a major stem, then we at least have to take 2 of these vertices for vertex choosing for finding the dissolving set. Now, next comes the necessary and sufficient conditions on resolvability criteria of T square and T cube. I'm skipping these details. And next we move to the upper bound of T square. Now, upper bound of T square differs by 1 from lower bound. So that is exactly equal to beta T plus 1. And we have also constructed one example where beta T square exactly equal to this quantity, beta T plus 1. And it can be easily shown that it cannot be dissolved by less than this number of vertices. So here, as you can see, beta T is 2 here, but beta of T square is 3 here. Next, we move to the upper bound of T cube. Now, upper bound of T cube is varying from its lower bound by the number M, capital M, where capital M denotes the total number of major stems. So, for finding the upper bound of T cube, major stems play the important role. Minor stems are not important here. So,
you have 2 more minutes.
Okay. Here also we have given some example where beta t cube is exactly equal to its upper bound and it cannot be resolved by less than this number of elements. So beta t is 4 here and beta t cube is 8. And so these are the some useful references we have used. And thank you.
Good. Any questions? Anybody? Any questions? Good. Some interesting graph theory results. I'm glad to see that.
Thank you, sir.
You're welcome. Any questions, anybody? Well, if not, let's move on to the next talk. The next talk is by Manitipa Saga on co-maximal subgroup graph of a group.
Yes, am I audible?
Yes, you are. Yes, you are.
Is my screen visible?
Yep. Yep. Go ahead, please.
Okay. So, good evening, everyone. Firstly, I thank all the organizers of this conference for giving me this opportunity to speak here. Today, I'm going to discuss about graphs defined on algebraic objects. People defined various graphs on different algebraic objects like group, ring, vector space, and we will see the connection between graph theoretic and algebraic properties. So, the basic idea to associate a graph with a group that started with Cayley graphs becomes a very interesting research area in algebraic graph theory. Different graphs are defined on group, ring, and on vector space. Some prominent examples are power graphs, enhanced power graphs that are defined on groups. Zero divisor graph is defined on a ring, subspace inclusion graph defined on a vector space, and so many. Now, we are interested to solve a graph problem with the help of algebraic tools, and this makes us understand the structural properties of the graphs in a better way. So these things basically motivates a researcher to study this area. Now, today I'm going to discuss about one of such graphs named co-maximal subgroup graph that is introduced by Agbari, Miraftov, and Nikandish in their paper. The authors defined the graph in this way that suppose G is a group and consider the collection of all non-trivial proper subgroups of the group, name it as S. Now, the vertex set of the co-maximal subgroup graph that is denoted by gamma G, vertex set is the collection S, and two vertices, that means two subgroups, say H and K, they are adjacent if their product gives a whole group G. Now, although the definition shows that there is a possibility that the graph is that the group is infinite, but in this context we just only focus on finite groups. And another thing which follows from the definition that the graph is an undirected graph, because if there is a H from the vertex H to the vertex K, that means if HK equals to G, then also it follows that KH equals to G. That means there is a H from the vertex K to the vertex H. So it makes the graph undirected. Now, these are some examples of connected co-maximal subgroup graphs. We have considered the group K4, that is a Klein 4 group, and this is the corresponding graph gamma K4, which is a complete graph on three vertices. Here H1, H2, H3 are subgroups of order 2, and as any two subgroup of order 2 gives a whole group, so one vertex is adjacent with all other. This makes the graph complete. Next, we consider the group S3, and this is the corresponding graph gamma S3, which is a star. Here H4 is the universal vertex, and H4 is generated by 3 cycle, and H1, H2, H3 are generated by the transpositions. As the product of a 2 and a 3 cycle gives a whole S3, so H4 is adjacent with H1, H2, and H3. Next, we will look some disconnected co-maximal subgroup graphs. For that, we consider two groups of order 8. One is quaternion group and another is dihedral group D4. And these are the corresponding graphs gamma Q8 and gamma D4, where in gamma Q8 there is an isolated vertex and a cycle with 3 vertices. And in gamma D4, there is one isolated vertex, H1. And in another connected component, there is a universal vertex, T1, that is a subgroup of order 4 generated by rotations. So, from these examples, we can see that there is a possibility of occurring isolated vertices in the graph. So, a natural question comes in the mind that can we precisely classify all those subgroups which correspond to isolated vertex in the graph? Now, this theorem gives an answer to this question, that if G is a finite group and H is a non-trivial subgroup which lies inside phi G is Fratini subgroup, which is the intersection of all maximal subgroups. So if H lies inside phi G, then H is an isolated vertex in the graph gamma G. And to hold the converse part, we need to give some extra condition on the group. If the group is nilpotent and H is isolated vertex in the graph, then only H lies inside the Fratini subgroup. It is to be noted that if we drop the condition G is nilpotent, then the converse may not hold. As an example, that consider the group A4. A4 is a solvable but non-nilpotent group, and its Fratini subgroup is trivial. So when we look into the graph gamma A4, it consists of a star along with 3 isolated vertices. But these isolated vertices are not inside phi A4 because it is trivial. So when we drop the condition G is nilpotent, the converse part of the result may not hold. Another thing, that if we consider our group G as any of our familiar known groups, does it graph give us any interesting property? So here we have considered G as a finite cyclic P group. Then the corresponding graph gamma G is ageless. There is no age, just only vertices. Again, for the converse part to hold, we need to give some extra condition on the group. If the group is a solvable group and the graph gamma G is ageless, then G is a cyclic P group. An immediate remark can be drawn from this result, which shows that the solvability condition in the converse part, it cannot be dropped, because as an example, if we consider G as projective special linear group of degree 2 over the field with 13 elements, then the graph gamma G consists of only isolated vertices. But G is not a cyclic P group. Also, G is non-solvable group. So when we drop the condition G is solvable, then the converse part may not hold. Next, we look into the connectedness of the graph, as we know that connectedness is a very important property. So here in this result, we want to characterize that when the graph, comaximal graph gamma G is connected. So the result says that if G is a finite group and the group has a maximal subgroup which is normal, then the graph is connected apart from some possible isolated vertices. That means, although there is a possibility of occurring isolated vertices, okay, but when we ignore those isolated vertices, there is just a single connected component remains in the graph. Moreover, if the group is an nilpotent group, then the diameter of the component is less or equals to 3. So an immediate corollary can be seen from this result, that if G is a finite solvable group, then the graph is connected apart from some possible isolated vertices. This holds actually, because in a finite solvable group, there always exists a maximal subgroup that is normal. So just by using the previous theorem, we can immediately solve the corollary. So what we have seen that so far, we have a group, we have corresponding comaximal subgroup graph gamma G, and if the group G has a maximal subgroup which is normal, then ignoring the isolated vertices, gamma G is connected. So this observation leads us to define a new graph that we call deleted comaximal subgroup graph, as we further want to study the connected component of the graph. So the deleted comaximal subgroup graph, which is denoted by gamma star G, this is just the graph obtained by removing the isolated vertices from the graph gamma G. And If G is a finite solvable group, then the graph gamma star G is connected, which follows from previous corollary. Moreover, if the group is a nilpotent, then the diameter of the graph gamma star G is lesser equals to 3, and the two graphs gamma star G and gamma G are same when the Fratini subgroup is trivial. This is true because for nilpotent group, when the Fratini subgroup is trivial, we have seen that the isolated vertices lies inside the Fratini subgroup for nilpotent group. So when the Fratini subgroup is trivial, there is no isolated vertex. That means the two graphs are same. Now, for finite solvable group, we can say that gamma star G is connected, but we want to look for something more. That means if G is any non-solvable group, whether also we can say that the gamma star G is connected. So this remark says that if we consider the group Sn, which is a symmetric group on n vertices, this is a non-solvable group, but Sn has a maximal subgroup n, which is also normal. And therefore, we can say that gamma star Sn is connected. So thus we can say that there exists a finite non-solvable group such that gamma star G is connected. Now, here we want to characterize the properties of the graph gamma G. So we want to look that when the graph is a complete graph, when it is a star graph, when the graph has a universal vertex, all these things. So the graph is complete if the group...
There are 2 more minutes.
Yeah, the graph is complete if and only if G is isomorphic to the direct product of ZP cross ZQ. It is a star graph, K1P, if and only if G is a group of order PQ, where P and Q are distinct primes and P greater than Q. And the graph has a universal vertex if and only if the group is a non-cyclic abelian group of order P square, or G is a group of order PQ where P and Q are distinct primes. Here we have characterized the universal vertices of the graph gamma star G. So if the graph has a universal vertex, then G is isomorphic to one of the following 7 groups, where the first 3 groups are abelian and the last 4 groups are non-abelian, which consist of dihedral groups, generalized quaternion groups. So what we have that G is a group such that the graph gamma G has isolated vertices. So a natural question arises that whether there always exists a group H such that gamma star G is isomorphic to gamma H. But the answer is no. And this is a basic important reason to study the isolated vertices in the graph. So as an example, when we consider the group G as P square Q square, which is a cyclic group, then the graph is actually a square along with 3 isolated vertices. And when we delete the isolated vertices, it is just a square. But this result, this theorem says that we cannot have a finite group H whose comaximal subgroup graph is isomorphic to C4. So this gives the answer to this question. Next.
I think it's almost time, so try to finish it.
Okay, yeah, give me just one more minute, please. Here we want to look here we want to characterize the group from the properties of graph. So if G is a finite group such that the independence number is lesser or equals to 8, then the group is a solvable group. Now some questions that we are yet to solve, that if G is a finite nilpotent group and with trivial Fratini subgroup, then we have seen that the graph has no isolated vertex. So we are curious about that. Does there exist any finite non-nilpotent supersolvable group with trivial Fratini subgroup and the graph has isolated vertex? Next question, that does there exist a finite non-solvable group for which the deleted comaximal subgroup graph gamma star G is disconnected? The third one is the interesting one, that if we have 2 different groups Z6 and Z15, then their comaximal subgroup graphs are basically isomorphic. So non-isomorphic groups can have isomorphic comaximal subgroup graphs. So this leads us to the question that under which condition the isomorphic condition on graphs implies that the groups also isomorphic. So these are the references of my presentation. Thank you everyone for listening.
Thank you. Very good presentation. Really deep, good results. Any questions? Quick questions? All right, let's move on to the next talk, a little behind. Next talk is by Santosh Biswas.
Okay, sir.
The topic is effect of awareness program on diabetes mellitus fractional order model solving by homotopy analysis method. Please go ahead. Santosh.
Sir, is it visible?
Yep, you are visible, you are audible. Go ahead, please.
Myself, Santosh Biswas from Department of Mathematics, Jadavpur University. The title of my presentation is Effect of Awareness Program on Diabetic Mellitus Fractional Order Model Solving by Homotopy Analysis Method. These are the outlines of my presentation. Diabetic mellitus is a complex group of non-communicable diseases caused by a number of reasons. Individuals suffering from diabetes have hyperglycemia because either there is a lower production rate of insulin or body cells do not produce enough insulin. The number of diabetic patients in the worldwide has increased fourfold since 1980. This rapidly increase contributed by population growth and aging, but there are so many things which are also responsible for it. Who states that in 1980, there are only 108 million diabetic patients, surpassingly today is reached to 422 million. If this trend is going on, the number of diabetic patients is reaches to approximately 628 million by the year 2045. Using fractional calculus, we have tried to explore the past behavior of the individual in prison regarding the diabetes. In the present study, we propose and analyze an effect of awareness program on fractional order diabetic mellitus model solving by homotopy analysis method. This is our model. In model, SU dashed, SA dashed, X dashed, and M dashed represents the unwashed susceptible human, our susceptible human, diabetic human, and cumulative density of awareness program. A dash is the constant rate of immigration in the unwashed susceptible human. Lambda dash is the rate of awareness program, that means susceptible, unwashed susceptible human become aware at a rate lambda dash. Beta dash represents the incident rate of diabetic mellitus, and beta dash beta 1 represents the lower incident rate of diabetic mellitus due to awareness present in the system, and where beta 1 lies in between 0 to 1. D and E dash represents the natural death rate, and E dash the additional death rate due to diabetics. And mu dash represents the coefficients of awareness program, and E dash prime, this represents the depletion rate of awareness program. The system has to be analyzed with the positive initial conditions. Now here, the system has to be dimensionless by using this type of transformation, and their corresponding parameters are these. Then the system one reduced to this system. Diabetes is a behavioral disease. Many behavioral factors play an important role in making diabetes more complicated in human body. People's past behavior may seem rather obvious to influence the future behavior decision. Thus, our modeling phenomena depend on previous time, which can be successfully achieved by using fractional calculus. In this study, we would like to analyze the fractional diabetic awareness model by replacing the fractional differential operator to the linear differential operator in our previous model system. And this is our fractional diabetic model, where delta dash mu I, where I equal to 1 to 4, this represents the fractional order derivative in the sense of capital differentiation, and mu I lies in between 0 to 1. Now we apply the homotopy analysis method, and we considering the following nonlinear differential equation like N1, N2, N3, N4. And next we get the zeroth order deformation equation like this equation here. This is not P, this is Q, 1 minus Q of this expression, this representation, and subject to the initial condition like this. Next, we expanding Q1, Q2, Q3 in terms of say Maclaurin's LC's expansion of with respect to Q, and we get the power series representation. And this is the power series representation with the last term. This is quantity is represented by this. Next, we choose each in such a way that the series will be convergence at a Q equal to 1. And then we can write the homotopy solution method by this expression SUMT equal to this representation. Next, and we consider the mth order differential mth order deforming equation like this equation subject to the condition this. And then we can write say SUMT equal to this equation and so on. And finally, up to mth order approximation, psi SUM and psi dash SA, psi just 5, and all these is nothing but this is the approximate solution up to the mth order of unsusceptible human, or susceptible human, diabetic human, and so on. Now, this is our homotopy series solution. This is depend on the physical variable D as well as the convergence control parameter H. The parameter H can be chosen so that the interval of convergence and increase the rate of convergence, and that reaches the solution at a quick rest. And we can apply first the square residual error method, and next we apply in the ratio approach method. And in the square residual error approach method, this method, and we can write this as the error function like R, SU, and so on. All these things are error function subject to the conditions like this. This is. And this is the another method like say ratio approach method. We calculate the beta where beta is less than 1, and d beta, the derivative of this quantity, this is equal to 0. Now, throughout our numerical simulation, we consider this set of parameter values. Most of the parameter values are taken from some different literature. And in the case one, we consider the ordinary differential equation. That means when mu I all this quantity are say 1, then this is nothing but this is the ordinary differential equation. And we can write phi SUK, this is the approximation solution up to 8th order. This is h to the power 8th order approximation solution of our human. This is our human, and this is diabetic human, and this is the cumulative density of awareness program. And in this figure here, x-axis this represents the value of h, and y-axis this represents the square residual error function. And we observe that at that point, which is very close to the point minus 0.96, and a square residual error value, this is minimum value, and if we consider this point, we get a deleted interval, and in which the value which is greater than at the value of this quantity. In the same way, we can get the following table like say this, the component function and optimal value of each, and we get the minimum value of the square residual error function. In the same technique, we can apply for the ratio approach method, and we get the like in this table where value of beta, this is the optimal value of h, and we give the interval of convergence. Next, we consider the fractional order derivative model, and we could choose a particular value like say mu1, mu2 up to all this quantity. This is equal to 0.75, and these all are the approximate solution. Obviously, 8th order approximation solution of our diabetic as well as cumulative density of awareness program. In this method, we also calculate the value of each and their corresponding square residual error value, and we finally get the table like this. In the same way, if we apply the ratio approach, then where beta SU, this is represents the y-axis, whereas x-axis represents the value of each. In the same technique, we can get another table like this, where this is the beta curves, and this is the optimal value, and these are the interval of convergence. Now here on the left figure, this is represents the fractional order differential equation model, and this is the right figure. This is the ordinary differential equation model. And
take
here
2 more
this is the
minutes.
unsusceptible. Okay, sir. Unsusceptible human. This is our human. In the same way, we get this is the diabetic human and awareness program. And finally, we get a 3D figure. In this 3D figure, this is the particular figure like this. Here, these axes represents the time, and these axes represents the fractional order derivative, like say mu I, and this is the diabetic human. And we observe that when mu I equal to 1, this is the ordinary differential equation. And all these things, these are the fractional order derivative. And in this case, the diabetic human, as the awareness coefficient must be a fixed value, and as time increases, then the diabetic human decreases over time, but this decrease is a lower rate than with the ordinary differential equation. And conclusion, our study reveals that the awareness program may minimize the prevalence of diabetics by education and awareness. In addition, controlling the complication of diabetics by trained rural health authorities would be more helpful and needed to begin treatment as soon as possible. It is also observed that fractional order differential equation model system for mu I equal to 0.75, the number of diabetic patients decreases slower than corresponding to ordinary differential equation for mu I equal to this. People who are aware of diabetes and the cumulative density of the awareness program, but their perception from the past behavior sometimes influence their decision to repeat the behavior in the present time, such as diet, physical activity, sleep, stress, etc. So in this case, the number of diabetic patients decreases slowly due to the past behavior of the individuals. These are some important references. And thank you.
Any questions for Mr. Biswas? All right. There are no questions. Let's move on to the last talk of this session. It's by Mr. Manoj Vadalai. The topic is mathematical modeling and performance evaluation of flat plate solar collector. Please go ahead.
Good evening to the respected chair and all the members of this session of 15th International Conference on Mathematical Sciences for Advancement of Science and Technology. I think I am audible and...
Yes, you are audible. Go ahead.
Okay, thank you. So also I am thankful to the organizer of this conference for considering my paper in this session. So the topic of this small talk is the mathematical modeling and performance evaluation of a flat plate solar collector. So myself, Manoj Bordoloi, from the Department of Mechanical Engineering, Tezpur University, India. So these are the contents of this presentation. First of all, the introduction and objective, and then the modeling and mathematical formulation, and then results and discussion, and then conclusions and references. So in the introduction, as we know, the solar, nowadays, the whole world is actually facing the energy crisis. So the every country is actually going towards the application of renewable energy, and the solar energy is one of that renewable energy. So the solar collectors are basically some devices that those are used for collecting the solar energy or in any type of solar heating systems. So generally, solar collectors are of two types. One is the flat plate collector, and one is the concentrating type of collector, like parabolic trough collector and all. So here I am, this work is the basic formulation and performance evaluation of the flat plate collector only. So here the objectives of this work is mainly the modeling and of the plate collector, and then the performance study of this plate collector, mainly the evaluation of collector thermal energy gain and the collector efficiency. So this is the simple modeling of the solar plate collector. So if we see here, this is the solar 2D view of the solar plate collector. Here the various components are shown over here. The first part at the above is the glass cover, and then one absorber plate is given, and after that the certain tubes are placed through which actually the fluids are passing, that is to be actually heated up by the solar energy. And after that this region is a insulation portion actually. So if we see the model of this collector, that if we consider that solar energy is 100% that comes from the sun, then in this glass cover 10% is actually reflected back to the surrounding or the environment, and 5% is absorbed on this glass cover, and then the remaining 85% actually transmitted towards the absorber plate. And then from the absorber plate, again 5% energy is again reflected, and then the remaining 80% is absorbed to the next fluid tubes through which actually fluids are passing. And then again from there only 80%, it is out of this 80%, only 45% is collected as our useful heat, and then the remaining 35% again lost to the surrounding and all. So now the mathematical relations or formulations for this model, generally if we talk about the thermal energy that is collected in the solar plate collector, can be obtained in using this relation. This is Q U, this is the useful heat gained in the collector, is equal to F into AC alpha multiplied by tau Zs minus UL, and this is the temperature difference, Ti minus Ta, where Ti is the inlet temperature in the fluid, and this Ta is the ambient temperature that we generally consider as the environment temperature. And here this F is as a factor called the heat removal factor, and that can be again obtained using this relation. F is equal to m dot Cp, where m is the mass flow rate, Cp is the specific heat of the fluid which is used to be passing through the tubes, and then AC is the collector area, UL is there is overall heat loss coefficient, and this 1 minus exponential of minus this term AC into UL into Fe. Fe here again the efficiency collector efficiency factor of the collector divided by m dot Cp, that is the actually heat capacity. This is mass flow rate and the specific heat. And then the solar radiation received by the collector is given by this equation, Qi is equal to Zs into AC, where Zs is the solar constant that is taken as a constant value of 1367 watt per meter square. Then the overall heat loss coefficient that we were talking about in the previous slide, that is UL, is given by AC plus HR, where AC and HR are the convective and radiative heat transfer coefficients between the collector surface and the surrounding. So here this AC can be obtained by using this relation 2.8 plus 3 times of US, where US is the actually velocity of the surrounding. Then HR, that is radiative heat transfer coefficient, it is epsilon H sigma. Epsilon is again here the hemispherical emissivity, sigma is a constant, again Stefan-Boltzmann constant. Then TP squared, it is plate temperature, and TA ambient temperature, and TP plus TA. So this is how this type of equation can be obtained. Then finally, coming to the thermal efficiency of the collector, that is given by generally the Q useful, which is actually obtained, or that output energy that we can say divided by the Qi. That is the inlet heat on the collector. And this using the previous equations, the efficiency can also be obtained from this equation number 7. We can get the efficiency as F into AC whole into the alpha. Alpha here is the absorptivity, then tau is the transmissivity, ZS solar collector minus UL. This is overall heat loss coefficient into the temperature difference between inlet and the ambient temperature divided by the solar collector, solar constant, that is ZS, multiplied by the collector area. Then again, in the simplified form, we can get the efficiency as F into alpha into tau minus F into UL into this temperature difference term. Okay, so these are all the equations that can be considered as the governing relations for simulation of to get the performance evaluation of the collector. So now, based on these equations, we have some results, and we can see from here that this first figure, this is figure number 3, is showing the collector energy gain versus the overall heat loss coefficient for different collector area. If we take the collector area as 0.1, 0.3, 0.5, 0.7, and so we can see that in all the cases, the collector thermal energy is reducing or decreasing, while the overall heat loss coefficient is increasing for all type of collector area. But here we can see that whenever the collector area is higher, then naturally the collector thermal energy is also higher, but they all decreases at the moment of increasing the overall heat loss coefficient. And if we go to figure number 4, here we actually use the different type of fluids which will be passing through the tubes placed inside the collector. This plot is showing the variation of collector thermal energy again with overall heat loss coefficient. So in these cases also we have seen that collector thermal energy is decreasing in all the cases, I mean for all the fluids. And here we have taken 7 different types of fluids, and we have seen that although these are all decreasing, but the collector thermal energy again becomes higher in case of the fluid in which the specific heat is higher. For example, here we have found the ammonia. For ammonia, it is higher, and then this way is gradually comes down for the fluid which lesser and lesser specific heat. Then this plots showing the variation of collector thermal energy and efficiency with the mass flow rate of the fluids that is passing through the tubes. So here the thermal energy gain is actually increasing in the logarithmic form for all the fluids again. Here also we are considering different types of fluid like methyl alcohol, ammonia, water, milk, etc., etc. So here we have seen that this thermal energy gain here also it's becoming higher or placed at the top level for higher specific heat. Similarly, if we talk about the variation of collector efficiency with the mass flow rate of the different fluids, then here also the collector efficiency is increasing as the increase of mass flow rate, but this increment is not much significant. However, we can show that these are increasing for all the fluids, and here also the same thing is happening, that for higher specific heat fluid.
You take a minute or 2 maximum.
Okay, thank you. So this is last result slide. So here collector efficiency variation with the collector area. In this case, the efficiency is decreasing for all the collector area. Increasing the collector area for different types of fluids again. And the last slide is showing the collector efficiency variation with the temperature difference. But here we are getting one interesting result that for a fluid with higher specific heat, it is decreasing as the increase of temperature difference. But as we going back to the fluids with lower specific heat, then it first increases and then it starts decreasing only. But however, this percentage of increment and decrement is not much significant. However, we can show that these are the variation with the with the temperature difference of the with collector efficiency. So these are some results, and based on that, the conclusions can be given as the collector. First of all, the collector thermal energy reduces with the overall heat loss coefficient for all types of the fluids. Secondly, collector thermal energy increases logarithmically with the mass flow rate of the fluids. And thirdly, collector efficiency increases with the mass flow rate of the fluids, but it's not much significant. However, collector efficiency decreases slowly, but with increase of collector area in all types of fluids. Then finally, the efficiency of collector decreases with the increase of temperature difference for the higher specific fluid, but for the lower specific fluid, it first increases and then decreases. And then collector efficiency and thermal energy all are actually are always higher for the fluid with higher specific heat. So these are some conclusions, and then these are the references from where I have taken this, the idea of this work, and then thank you.
Any questions, please? Well, if no questions, wonderful talks, really nice results. Thanks all the speakers.
Thank you.
So let's thanks our chairman chairing this session, Professor Manikam. Thank you very much for chairing the session, and all the 7 speakers that we had. Thank you very much for all the nice presentation. So we just 5 minutes running out of time. So quickly I will switch to the next session. And I'm glad to inform you that three of the speakers already joined with us. First speaker will be Professor Shuhit Dey. I can see him. Yes, I can also see Professor Mukherjee, Bagisha Mukherjee. She is also here. Nice to see you again. And Carl Schupp, I think he is getting, Carl Dettridge is also here. And the last speaker is Carl Schupp. He is chairing a parallel session, so he might be joining us shortly. So without any further delay, may I just request Professor Dey to please share your screen so that we can start directly without having any delay. Yeah, could you please unmute yourself, Professor Dey? You are muted.
Can you hear me now?
Yes, we can hear you. Yeah.
You can hear me?
Yes. Could you please share your screen now?
Oh, okay. Share my screen.
Yes, that arrow box.
Okay.
Yes.
Your screen.
Your entire screen. Then you need to click on the box, not on share or cancel. Yes.
I did.
Yes. Done. Great.
I'm done?
Yes. We can see your screen. Great. Very easy.
Can you hear me?
Yes, we can hear you. Yeah.
Okay. Can you see this?
Yes, of course.
Okay.
So may I now request Professor Shuhit Dey to please start your lecture. The title of his talk will be Numerical Studies of Berger Equation by PFI with applications to Berger's equation representing flow models and with and without multiple shocks. So without any further delay, sir, the screen is yours.
Oh, can you see the screen now?
Yes, fine, perfect. And we can hear you as well.
Good. Again, thank you, Vishek, very much for organizing this interesting meeting. My talk will be short and simple, hopefully, mostly mathematical. Let's consider first a simple nonlinear equation, and that can be represented like x equal to g of x. Very simple. It's just one variable. And if you use Picard's iteration, the simple one, then it will be like if x sub k represents the value of x at the kth iteration, then x sub k plus 1, that means the next iteration, is equal to g sub k. There is no omega sub k in Picard's iteration. All that I did is something very, very simple. I added a perturbation parameter. This is a baby of mine born in 1971 inside my class when I was requested by students to do an assignment that I gave them to do. Anyway, question is, what is this omega k and how we can compute that? The computation formula is rather simple. I've got lots of publications where all these things are discussed in details. Now, if we assume that it converged at k plus 1th iteration, then this relation must be true, which means omega sub k plus g sub k is g of this, because this is xk plus 1 and this is x sub k plus 1. The both must be the same. And using this formula, we derived omega sub k, which is very simple. And then wanted to do some interesting problems. And this is one of the interesting problems that I solved, that if you assume that this is an equation, these equations appear sometimes in a fluid flow model. And then you look at this solution, how omega sub k work. If this is x sub 0, Picard's iteration, Picard will go to the curve, and from curve it goes to the line, then goes to the curve, and so on. Now, if you look at the curve, and if you look at the slopes of the curve, then it is obvious that it does not follow Lipschitz condition. Picard's iteration converges, and then a sufficient condition is it must satisfy Lipschitz condition. Obviously, it did not. So Picard's iteration didn't work, and Newton's method also didn't work, the standard method. This was my assignment that I gave in the class. It's an undergraduate class. And I asked them to express this equation as x is equal to x minus 2 times tan inverse x. And that is, I asked them to take initial guess equal to negative 1.5. That is the end of the class, and therefore I was in a rush to go. But the students come back to me and said, Picard's iteration did not converge, moved around. You see, it goes from the curve to the line, from curve to the line, and moves around. And Newton's method miserably failed because it takes the tangent line, goes there, it takes the tangent line, goes all the way over there, and so it didn't converge. Both failed. And student asked me in the class to do my assignment, and I figured out that perturbed functional iteration and did it right here, in short, which means this is my initial guess. It didn't go to the curve. It in fact went down. That is the difference. That is the omega factor. And I don't want to go too much on that. Then I decided to solve nonlinear system. For nonlinear system, the equations look like that. Dn is where x belongs to. It is a subspace of R super n, which is the real n-dimensional space. And these are the Picard's iterations. But what I did, I computed my iterations applying omega sub k to the systems of equations. This is system of equation. And the formula to compute omega sub k I figured out. This is the formula. Now you look at that. This partial dg super k, that is a diagonal matrix. So this diagonal matrix, I is the unit matrix. Easily I can invert that. Therefore, this inversion is really simple. And we found that under proper values of omega sub k, or proper representation of g, we can solve this equation. And meaning, this means, and look at that, d superstar means that this is the region where the solution exists. And this region is basically what we call, forms a Banach space. If you look at this only this form, that there is a series of contraction mapping. And this contraction mapping I found doing what we call demapping that I developed many years ago, I think in 1978, at Von Karman Institute for Fluid Dynamics in Brussels, Belgium. And then I applied it massively to fluid flow problems at NASA EMS. This mapping means the requirement that all functionals must satisfy Lipschitz condition, which is essentially a weak sufficient condition for convergence. I violated that, I bypassed that. This is the algorithm of PFI in n-dimensional real space. And this omega going to zero is actually a necessary and sufficient condition for convergence. And we bypassed this stringent condition that it must satisfy Lipschitz condition. Obviously, if we look at that this is essentially metric-free. And as we approach convergence, the diagonal linearization, which I did to compute omega, because omegas are going to be damped out. The all diagonal linearization will be damped out. And we also see, if you look at this, that PFI, this is a vector, that means it is a vector process. That means we took an entire vector and transferred back to another vector. And that is why we say it is a fully vectorized process. And most interesting thing is that we can use MPI, message passing interface, and solve massively large-scale nonlinear models. And I applied that in my project solving reaction diffusion equations when we studied breast cancer treatment computationally. And my monograph will be published soon, hopefully, by Springer Nature. Now let's go into the Burgers equation. Motion of viscous time-dependent flow models have been described by Navier-Stokes equation, which are nonlinear parabolic partial differential equation. These are generally solved by numerical methods because analytical solutions are often extremely difficult, almost impossible to find. We will consider first Burgers equation, approximate them by implicit finite differences, thereby forming a nonlinear system, and solve them by PFI at each time step. The primary reason to use implicit finite differences is that they have much better stability properties. Let us consider first Burgers equation in 3 dimensions. When Burgers invented this equation, he thought he is developing a turbulence model, but that's not quite right. This is Burgers equation in 1 variable, but in 2 dimensions and 3 dimensions. And it has an exact analytical solution, and that is this, which I figured out. And if you know the analytical solution, if you can figure out, then you know under what boundary conditions and initial conditions these things are happening. Now, the steady state solution, the interesting thing is, if t goes to infinity, if you look at this, is exp means e to the power, it goes to infinity, this goes to 0. This goes to 0, means ultimately this will be damped out. Therefore, but at t equal to 0, if you look at t equal to 0 and you see what is happening, that this happening, is when, if you put t equal to 0, which is the initial condition here, but if you put mu equal to 0, take a look at that, when mu is equal to 0, this is a very interesting point, because some people, especially at NASA, they often introduce mu and call it artificial viscosity. I'll discuss it very soon. If mu equal to 0, we go back to the initial condition. That is the solution. And I validated that I can substitute that form of solution into the equation and see that it satisfies this equation. This solution under given initial boundary conditions of nonlinear equation behaves almost like the heat equation. Although this analytical solution is not applicable to one-dimensional Burgers equation, unfortunately, in one-dimensional Burgers equation, if you look at the reference one is a book by Bill Ames. It's a numerical solution of partial differential equation, a very famous book published by Barnes and Noble. And 2 is my paper, which appeared in Journal of Computation and Applied Mathematics, I think way back in 1977. I can, from here, going back, from here, we find out that a generalized solution of Burgers equation, if you consider this equation, this is in n dimension actually, I dimension, but with one variable to see how E is behaving, and this is the analytical exact solution. But there are other exact solutions depending on your initial and boundary conditions. Now, if you consider again mu going to 0, mu is 0, it means the solution is simply this one, from here to there. That is the solution. And if t goes to infinity, solution will be damped out. That is the property. And this is my article, I guess. Yeah, that's the article. Now, what the problem is here, when there are flows, can I go back to you? When there are flows, and if you see, one flow is going above, one flow is going below. Interaction, like for tornadoes, one flow is moving this way, other flow is moving that way. The opposite direction simultaneously is happening. Then the method that I represented, or method that most people they used, they do not work. PA5 miserably fails. All these techniques fail. So we go back again, that we consider, again, a simple example, like one-dimensional Burgers equation, to see only the flow, one flow is above, one flow is below, or the interaction of shock waves. The shock waves go one, if you think of supersonic flight, one shock goes there, one shock coming from here underneath, The interaction of shock waves. One is called the refraction shock, the other is the regular shock. If we do that, then most methods that we know in computation fluid dynamics miserably fails. At NASA Ames, two very famous scientists, Joe Steger and Bob Warming, my very good friends, Joe passed away a few years ago, developed flux vector splitting. That means we will follow the motion of the shock. We will follow the motion of the velocity, where from flux is coming. And I guess, and they use matrix inversion technique to solve this model. And I used PFI to solve exactly the same model. And my solutions are as good as theirs. And possibly, I think, better because I don't have to use what is called just a second, what is called artificial viscosity. I did not. And here is the model. U sub I is equal to G sub I super N. This is the nonlinear system here. And G sub I is expressed like this. I express this conservative form of the equation in this form. And if you look at that, this form says that wherever wind is blowing, in which direction wind is blowing, we will follow the wind. That's what we will do. And if you do that, then the solutions look very, very excellent. And I'll show you the solution now. If you give me a little time, hopefully it will come. Let's go into program 1, and I will show you first what other solutions do. You see, most solutions, Abhishek, can you see this screen? Hello? Abhishek?
Yes, visible.
You can see it?
Yes, yes.
Okay.
Yes, we can see it. Yes, fine. Yeah.
This is overshooting, undershooting. See, one fluid is moving in this direction towards the positive direction of the x-axis, positive direction. Just below that, another set of wind motion is taking place, moving in the negative direction of the x-axis. And 99.9% of the times, the method that people use all over the world, they cause this problem. This is overshooting, means going up, undershooting, going below. And finally, of course, I use my PFI to solve this. And you see, PFI works in the steady state, but obviously it doesn't do the kind of job that we want to see, that analytical solution shows that should happen. Now, I will go back there, I'll reduce this, and then go to program number 2. Now, this is where I used, excuse me, I'm taking a little bit of your time. This is with PFI flux. It is now flux vector splitting. And this is for Abhishek, number 1, always first class first. That is FF. Now let's do the solution, and I want to show you how it looks like. Now let's see, I will take this case. Look at that, what happens. See, there are multiple, not just only one flow, multiple flows. One flow going this way and other flow flowing like this way, like rotating fluid, which happens in seismic waves, in earthquakes, in tsunamis, which happens when there are interaction of shock waves and all these things. Look how smoothly, there is no overshooting or undershooting. And see, the GNU is 0, which means I did not add any artificial viscosity to stabilize. Look at the DT, delta T, always people use it much smaller than delta X. I use delta T more than twice larger than delta X. And here it is. Now let's take another equation, and that will be number 3, I guess. I guess this is number 4. Yes, look at this. Look at this motion. Here, the interaction, the flow here, the U is carrying, energy is a lot more from here to here. Then there is a shock. And then energy is a little less here. Then there is a huge shock here. And this is the refraction shock. It goes like this. And then it moves up. Again, this is a shock here. Look at that. Then there's a shock here. That is the initial condition. But all these things will be damped out because that is the majority of energy that will flow this around the positive direction of x-axis. And it goes like that. See how many discontinuities are there. And I considered, forget about Reynolds number, this is not Reynolds number 0. Reynolds number is infinity. And look how the motion is going around. There is no overshooting, there is no undershooting. And I guess this is the end of my talk. I wanted to be brief. I hope I have finished in time. And if you have questions, feel free to ask me.
Yes. So any question or comments, both from YouTube viewers as well as live viewers in Google Meet? If you have any question or comments, please, those who are on Google Meet can directly ask questions, and those who are on YouTube can ask through chat.
Feel free if you have questions.
So nice presentation. Few comments that I'm getting from YouTube. Okay, so
any question, Abhishek?
No question yet. So maybe after some, after some time.
If you have questions, feel free. Abhishek has all the information. You can write to me. Hopefully this will appear in a monograph that I'm writing now on PFI with applications in engineering and applied science.
Okay, if there is no further question, let's thanks once again, Professor Day. Thank you very much.
You are most welcome, Abhishek.
Thank you. So now may I switch to our next speaker, Professor Bhagisha Mukherjee from Penn State University, and the title of our talk will be Defect Structures in Liquid Crystal Flows. So over to you.
Okay, Abhishek, can you hear me?
Yes, I can hear you.
Is it all right? Okay, so then let me first get to this one.
Let's see who is presenting. Professor Day still, I think Professor Day is still presenting. So could you please stop presenting? Could you please present?
I'm not presenting.
Okay, maybe
Yes.
okay, then maybe.
No, I think he need to click stop present.
Could you please?
Okay.
Yes.
Go ahead.
Yes. Yes.
Okay.
Though,
Yeah, now
yes. Fine. Thank you. Though not presenting, virtually present.
Okay. Sorry, Bhagisha.
Oh, that's okay, no problem.
Yeah, right. I like to listen to you.
On the screen, so I selected this one. So, okay, can you see my screen? Is it all right?
Not yet. Not yet.
Not yet, but I can see mine. Should I try it again then?
Yes. Click on that. So you are from.
Okay, so it says select screen, right?
Yes,
So,
your entire screen, and then you
entire screen. Okay.
And then you'll have to press on the box where you find your own image. So you need to click there.
That's the inside the screen then.
Yes, inside the screen. Then you will find the share will be active.
I don't see it. What do I? How do I go there?
After you click in the smaller screen, then you need.
I did, but it's not. Okay, so the entire screen. Okay. So I click on the screen. Okay, so then I see a small screen.
Yes, click on.
And then no, it doesn't go there. So what do I do? Allow. Okay, so I said allow. Okay, so you can see my entire screen.
Now it's coming.
Now it's starting. Okay, so then I.
We can see your screen now.
Now, can you see it now?
Yes. You just need to make it full screen now.
No, can you see my screen now? I mean the actual my talk.
Yeah, I can.
Yeah, we can see.
Full screen means say.
Okay, so thank you, Abhishek. Thank you very much for giving me this opportunity to give a talk here. And I wish Dr. Odhikari was here too. But anyways, I am from Penn State Scranton campus, and today's my talk is on defect structure in liquid crystal flows. And I will basically present all like small results of defect structure. That's what I work on, and I put them together. Okay. Since it's not like regular topics, I'll give a bit of introduction here first. So in my outline, what I have is first I'll talk about the introduction and application, like how it started with like phase change in different materials and how we get liquid crystal and their application. And then I'll talk about a little bit of static deformation in liquid crystals and what are the elastic energy coefficient and how the boundary treatment works on liquid crystals. And then I'll talk about dynamics of pneumatic liquids, especially pneumatic liquid crystals, and what do we mean by defects in liquid crystal flows. And then I'll talk about small results in shear flow of liquid crystal, wet flow of liquid crystal, and extensional flow of liquid crystals. So what happened is, like in ancient ages, soft matter phase transition in Amazon basin. So they had this Havia tree, and that sap of Havia tree, when it comes close to air, then it makes it makes like a kind of material, like soft rubber kind. Okay, so that liquid, that sap, when network structure which can resist the tension, it becomes a rubber. It's a very mild chemical reaction happens there, and then it becomes like the air builds some links between the polymers, and then it drastically changes the property of the polymer, and that soft matter becomes complete fluid. And Pierre Digens got Nobel Prize on working on his work on liquid crystal in 1991. Now, we know that solid, which has like fixed position and orientation, and there are materials which are solid. Now, with increasing temperature, molecule becomes a little bit more random than what the structure was. So it becomes pneumatic liquid crystal, and then with increasing temperature, all the molecules are random, so it becomes isotropic. So we know that solid is like fixed position and orientation, liquid is no fixed position or orientation, and gas is like random. Now for liquid crystal, it has properties like it can flow like liquid, but it has some anisotropic property like solid. And then it has many applications in like synthetic and biological viscoelastic material that you can use those things. Now, we will talk about pneumatic liquid crystals here. Now, pneumatic liquid crystals are like they are like thread-like molecules, long axis, aligned parallel to each other in a preferred direction, like the picture that you have here. And these aligned molecules can translate freely, and rotational symmetry about the anisotropic material. Okay, so that is, we call it uniaxial pneumatic liquid crystals. There are others like biaxial and other types of liquid crystals also. Okay? Now, when we have these different molecules here, if we take their average molecular alignment, we define a vector. We call that director. Vector N is defined as director, and material is this fluid, so that is the preferred direction of orientation. Okay? And order is that measures the quality of alignment around N, and that is the order parameter. It's like locally, if we look at the molecule, how that molecule how closely related it is to, or what is the angle between the molecule and their average direction. So that's how we measure what is called the order parameter. Now, these are different structures of liquid crystals, defects in liquid crystals, and these are different materials which are polymeric. Okay? And this is courtesy to Kent State University. They have Liquid Crystal Institute, so these pictures are from there. And then there are other types of liquid crystals. So this is like cholesteric, which is called chiral pneumatic. Its structure is like DNA structure. So you have like a cylindrical axis, and then the molecules are around that. And there is usually pneumatic liquid crystal has mirror image symmetry, but chiral pneumatic doesn't have any mirror image symmetry here. Okay, and this this distinct right and left sides of the spherical structure, you can see that. Okay? And then there are other types which are called smectic liquid crystals. So this word smectic, in Greek it means soap. So it has layered structure. So pneumatic is also, it has a preferred direction, as you can see, but smectic has a little bit more layered, more order, as you can see here. So it has this, or you might have, the angle could be like a direction. There is an angle with the director and the vertical axis. So there are like different types of smectics and pneumatics, as you can see. And liquid crystals are used in a lot of places, like as precursors. It is like structural thing of liquid crystal we use for precursors, like fibers and films, foams, composites, blends. And as a product, functional liquid crystals are like as lubricants, radioactive media, actuators, electromagnetoradiological fluid, you can use it that way. And then electro-optics is like, liquid crystal displays and light bulbs, and a sensor, thermal liquid crystal, and then chemical and stress. For all of these, different types of liquid crystals and their properties are used. Now for static energy, liquid crystal, the director that is like N is the director. So this Osin-Frank energy equation has this form where this K1, K2, and K3, this energy expression helps us to measure the deformation in liquid crystal. So K1 represents the splay type of deformation, which is this kind like a fan-like structure, and K2 is the bend kind of deformation that you can measure with that, and K3 is the twist, which is like this one, okay? And this K1, K2, K3, these are called elastic constants or Frank. This expression is due to Osin-Frank, so these are all sometimes called Frank constants also. Now about the anchoring, like liquid crystals on the boundary. So this bulk energy is supplemented by surface energy, and how N is aligned at the boundary of the domain, that is what is called anchoring. So you can have different types of anchoring. I tried to give you some examples here, like conical anchoring. So the director has a fixed angle with the boundary, or it could be weak anchoring, that means there is no preferred, direction at the boundary, or it could be strong anchoring. So that means maybe the director is like, you can have homogeneous boundary, which is like they're parallel to the surface of the boundary, or it could be like homeotropic, which is like perpendicular to the surface of the boundary. So we can have different types of boundary conditions. And what happens is, this is what we can say like nematodynamic cycle. So there is a flow, and due to the flow, there is those molecules, their orientation changes. So this is like flow-induced orientation. And due to that change, there is some microstructure kinematics evolves there in the flow. And because of that, there is this orientation in the induced flow. So because of the flow, there is a change in the orientation, and because of the change in the orientation, there is some flow is created. So that's how this whole thing goes. So, and that is the reason it's really hard to study. So this is like the nematodynamic cycle. Now these equations are due to Erickson and Leslie. These are we are using a continuum model for nematic liquid crystal. So here our assumption is that it is incompressible. So divergence V is the velocity. So divergence of the velocity is 0. And then for director constant, we take that director N is a unit vector. And then we have the conservation of mass and conservation of momentum equation here. This is Navier-Stokes equation. Rho is the density and sigma is the stress tensor. Now this sigma, the stress tensor, it has the form like this pressure, and there is a viscous part. This one is not a symmetric tensor. Okay, so this is the viscous part of the tensor and the stress tensor. And if you look at the viscous part, it has like this expression, complicated expression. All these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, these are properties of, these are called Leslie coefficient, because this equation is derived by Erickson and Leslie. And these are, they all depends on the properties of the material, liquid crystal material that we are working. And this A and capital, go to the next slide, you will see that. Yeah, this A is the rate of the stress tensor, so that is the symmetric part of the gradient of the velocity. And excuse me, capital omega is the vorticity tensor, which is the antisymmetric part of the gradient of the velocity. And capital N is the time derivative of this N. And this sigma B is these Leslie coefficients. They have, like, these are 6 of them, but there is a relationship here. This is called Parodi's relation, and that is again derived using properties of the material. So this is like, with this constraint, we can change from 6 to 5 independent Leslie coefficients, and then this rotational viscosity gamma 1, that is always positive, and then this torsion is measured by gamma 2. So these gamma, those K's are elastic coefficients, and these gammas are viscous coefficients. You can, think it that way. And Leslie angle, we have seen that if we do the calculation, this tangent square theta 0, this is alpha 3 over alpha 2, or if we write down the equation, the equivalently, it can be written like that. Now, velocity gradient aligns with Leslie angle in the bulk of the flow. Now, we say that liquid crystals which are flow aligning, product of alpha 2, alpha 3 are positive. So that means that we will have, as you can see here, we will have tangent square theta 0 to be positive, which gives us some real solution for theta 0. Whereas for non-flow aligning liquid crystal, this product alpha 2 and alpha 3 are negative. Okay. Now, there are a couple of things that what happens. It might happen that here the director comes out of the plane, there is some tumbling region, so all those things can happen. Now we define a second order moment of an orientation. It's just to measure the order parameter, and from there we will get the defects. Okay. So a second order moment of an orientation distribution function. So properties of this moment is M and M transpose, and trace of M is 1, and eigenvalues are all non-negative. Now, instead of M, we use this Q, M minus 1/3 of the identity tensor, and then for Q has these properties, some of the eigenvalues are 0, and -1 less than or equal to 3, Qn less than or equal to 2, or in other words, that's what we get. Now, if we have this Q distinguish 3 different kinds of configuration in liquid crystal, and that's where we are going to get the idea of defects. That is, Q equals to 0 is isotropic configuration, all Q1, Q2, Q3 are zeros. Now, if 2 of the 3 eigenvalues are equal, so then Q takes this form where that S has the value between -1/2 and 1. Now, S is the degree of orientation. That is where basically this is the measure of the order parameter. So that helps you to see what is the quality of the alignment with the director M. And if all three eigenvalues are different, which we get biaxial nematics. But here I will consider all the time uniaxial nematics, which means S is going to be between -1/2 and 1. Now, there is another quantity which is important in our study, which is called Erickson number, which is gamma over K. So this gamma could be gamma 1 or gamma 2, those viscous coefficients. And this K could be K1, K2, K3. Those are those elastic coefficients. So this is the Erickson number. So ratio of this typical viscosity over elastic coefficient. Now this measures the deformation of the director field under the flow. Now, high values of Erickson number means we'll say 1 over E equals to 0. Low is like this is close to 0. Now, low shear rates gives us stable state determined by anchoring. So elastic forces balance the small viscous stress. So we get like stable thing. And beyond the critical value of E, M attains a new in-plane tumble steady state. So for high Erickson number, that means high elastic energy, this tumble state is in the plane of velocity and velocity gradient. Or for even higher value of E, for very high shear rates, out of plane stationary state is possible. So there are experimental results, people have those, and here we will just explain some of our analytical work, which basically sees that people what they have seen in experimental result, we get the same result in our analytical work. So it supports the experimental result. So this is one of those. For shear pneumatic liquid crystals, in the presence of a magnetic field and in the asymptotic limit of high Erickson number, okay, Erickson's model shows there is a defect present in the flow. I didn't want to write all those equations and things here. Just wanted to make sure what happens is once we use those pneumatodynamic equations that we write this. We can go a little bit up here. Let's see. So I guess you have seen those equations. So those equations are from there, it is defined. I mean, we have written there in terms of the order parameter. And then we saw that in order to solve the system of equations, those conservation of mass and angular momentum, we write them down and we make them in order to have a solution for non-constant velocity field. We get that we have to have this condition. And you can see that if S is between -1/2 and 1, the only solution is S equals to 0. So S equals to 0 is the defect. So that guarantees that there is a defect present in the flow. Now, this approximation is valid in the bulk of the flow away from the boundary effects. And numerically, people have seen that chains show that some defects annihilate, whereas some are stable. Khoromskaya and co-authors show that defects leads to vortex structures in the flow. Kras and co-authors numerically show the formation of vortex in shear flow of pneumatics in the presence of magnetic field. And this is our preliminary work to show that yes, defect is present in the flow. And these are numerical and experimental work. And then we talk about Couette flow. Couette flow, this is the flow between two cylinders that we are talking about. So they are concentric cylinders, and we are using polar coordinates here, cylindrical polar coordinates here are theta z, and we are talking about in-plane velocity components. All our studies are in-plane. So we take the velocity to be this way, whereas the director n in this form, so that the unit director condition is satisfied, and the constant divergence of the velocity is 0 and n dot n equals to 1. So all of them are there. And these are the linear momentum and angular momentum equations. And once we simplify this, we get this equation. So I'm not going through all this. It's just that make sure that you see that we have these gammas here and this tree here. Those are the important ones in the expression. And we also have this g of phi. If you look at this here, this expression g of phi here, the g of phi is this big expression once we do all this calculation, and that has to be greater than 0 because of the second law of thermodynamics. And then the boundary condition, if you take strong anchoring condition, either they are, it could be homeotropic or this homogeneous or homeotropic conditions, and we take there is no sleep boundary condition for the velocity, and existence of this system is existence of solution is of this system is proved by Carter and Liu in 2000. And then we see that for steady state, so we take all of them just functions of r, okay, and for flow with low Erichsen number, governing equation becomes this, although if you simplify. Now, if omega r is 0, so we get the rigid body rotation, and omega r not equals to 0, this gives us cosine 2 phi is this, and sine 2 phi is 0. Now, this cosine 2 phi is that flow alignment Leslie angle. If you see that, this is the flow alignment angle phi here. And then just to make things simple, if we choose those two elastic coefficients the same, okay, usually they are same order, okay, then flow with low Erichsen number means we are taking that there's gamma over some gamma over k, so that we are writing it over to be 0. So these are what we get. And there we are trying to see that if we take, say, square phi apart is some function of r, because all of them are function of r, the solution of the angular momentum equation for the director becomes this. And moreover, you see if we choose phi r to be a constant, then that means phi is constant with respect to r. So then S becomes, you can get actually an expression for the that order parameter S. So this is our result. That is for low Erichsen number. If the director angle is a linear function of r, that's why phi sub r is constant, then defects in the flow at a distance r from the boundary can be expressed as, you can get an expression here, though there are some, as you can see, there are some assumptions, some simplifications. I mean, otherwise these are hard to study analytically. So that's why we had made these assumptions. And by low Erichsen number, you can think that the flow is slow, or maybe the gap between the cylinder is narrow, or the elastic energy dominates over the viscous energy. Okay, so this is the flow aligning condition. This is the Leslie coefficient, you know that. So then there are experimental results that Hoffman et al. In 2009, they have seen the existence of stable defects, and experimental and numerical appearance of stable defects in Taylor-Coe flow. They are there, and combine here what we are doing is we are combining continuum mechanics with molecular theory. So we are using the properties of those alphas also. So that's what we get. And then this is the, now I'll talk about extensional flow. So here we are taking this magnetic field with this expression where this, you can see that external field H applied to a pneumatic liquid crystal. Ocean-Frank energy equation, we introduce the magnetic field there also. So chi A is the magnetic susceptibility, and chi A is positive for pneumatics, and B is the magnetic induction. And again, the existence of solution is already proved. And for a flow, a channel, so we are talking about extensional flow with variable channel width. So it is, we are again talking about in-plane flow. So we take the flow expression like this so that it satisfies the divergence of the velocity is 0. And also we take the expression for the director to be like this so that the constraint is satisfied. And then the angular momentum equation with this energy equation, this is what we get, the angular momentum equation. And if you notice that this critical strain rate is this. So what they saw in the experiment is, we'll get there. So if you look at this expression, you see whether this expression is positive or negative. If it has to be remain the same, basically sign of sine theta has to change. Okay, so that's what we are saying here, that K positive means the flow is in a narrowing channel, K negative is flow is in a where the channel expands, and theta is always, I mean, this restriction is right at the beginning where we defined it. So changes sine theta. So sine theta corresponds to a flip in the director determined by theta becomes negative theta. So the main result here is for extensional flow of pneumatic liquid crystals in the presence of a magnetic field, the director reverses direction as a critical value of the strain rate is given by this. So for the momentum equation to hold, when the quantity changes sign, then sine theta needs to change sign accordingly. The director will reverse its direction at a strain rate Kc, which is determined by, if you set it equal to 0, you get Kc to be like this, and changing the director angle is equivalent to the director field flip. So that reported by experimental result by Cormier. They have done the experiment, and that is the result they have seen. So experimental results, Cormier et al. Used Leo Inemar to study director orientational behavior for ordered material under extensional flow. They observed and reported a distinct director field happens at a critical strain rate. So you can see the same thing here in our analytical work. And theoretical work, we consider a continuum model matching the requirements for the experiment and derive a theoretical critical strain rate matching their experimental result. And this result presented here is an in-plane steady state case. So these are like 3 different types of flows, all with liquid crystals, and all are just simple work, as you can see. Of course, there is a lot of calculation involved, but we can see with this simple analytical work that we can see those results that happens in experiments and numerics. And thank you very much for your attention.
Thank you, Professor Mukherjee, for your nice lecture. So any question or comments? So those who are on the Google Meet can directly ask questions. Those who are on YouTube link can ask through chat. I can transfer it to Professor Mukherjee.
Should I stop when I stop presenting them?
Yes, please. So if there is no more question or comments. Thanks once again, Professor Mukherjee.
Thank you.
It's my great pleasure. So without any further delay, may I directly switch to Carl. So Carl, the session is yours and the title of the talk will be Color Theory, Basic Color Model 6.0, Basic Music Theory. So Carl, the session is yours.
Hey, thank you. I just have to get oriented here.
Yes, very easy. To share the screen, you want?
Yeah.
Yes.
So present now?
Yes, present now. Then your entire screen.
Entire screen.
Then an image with your box will come. Click on that box on the, not on share or cancel. Click on the box, big box that came on your screen. Onto that, you need to click. Can you see anything, Kim?
Yeah, I see a box that says share your entire screen.
Yes. After that, when you click on your entire screen, what comes?
Okay, I need to click share.
Yes.
No.
No. Before that, you need to click on the big box that came. Your image and everything came. Just above share and cancel. Just above share and cancel. A big box is there on which you can see your screen itself. Click on that box and then the share will be activated.
I see a present now.
Okay.
I'll click on that.
Click on that. You see that your entire screen, right?
Yes.
Click on that.
A window, a tab, or your entire screen?
Yes, your entire screen. Click on your entire screen.
I did that.
And then what you see?
I see a box up at the top says share your entire screen.
Yes. Click on that box. Then share will be activated.
Okay.
Share is activating now?
Yeah.
Share and cancel. Yes, great. Done. Yeah, now we can see your screen. Yes.
Am I good?
Yeah.
All right. I just need to. All right. So I'm ready to go.
Yes, please.
Okay. My name is Carl Swopes, and I'm working with color research that I'm attempting to describe or define color in terms of numbers and geometry. So it's taking me down a different path versus looking at visual colors. So basic color mechanics research has predicted that color is applicable to the entire electromagnetic spectrum, not just the visible light spectrum. It has defined a color model in the range of audible sound per subharmonics of the visible light color models, primary red anchor, and total range baseline values. Therefore, the concept of color and the associated color mechanics are scalable. The frequencies associated with sound are also found in the electromagnetic spectrum. Music is a tonal arrangement of sound. There are 12 primary tones in the equal temperament chromatic scale. The color hexagram identifies 6 primary colors and 6 interfaces. Sir Isaac Newton developed a color wheel and assigned musical tones to the colors. This color research will identify a geometric and numerical correlation between the color hexagram, the circle of fifths, and the A440 method of tuning per the similarities between a music octave and Jacob's ladder. Jacob's ladder harmonic, which I have called the color octave to differentiate it between the music octave. The circle of fifths music theory. Per the total range of a defined color model, the 6 primary colors are spaced 1/6 of the total range of each other. The range of an individual primary color is also 1/6 of the total range of the defined color model. The primary color is the frequency that sits at the center of its range, with 1/12 of the total range distributed above and below the primary color. Per this color research, the primary red anchor is located 1 times the 1/12 value from the system 0. Subtracting the 1/12 value from the primary red anchor value identifies the 0 for the defined color model. From the color model's 0, primary colors are found at 1 times 1/12, 3 times 1/12, 5 times 1/12, 7 times 1/12, 9 times 1/12, and 11 times 1/12. From the 0, the interface points between primary colors are at 0, 2 times 1/12, 4 times 1/12, 6 times 1/12, 8 times 1/12, 10 times 1/12, and 12 times 1/12. With the 1/12 spacing, the reference positions are like the numbers on the face of a clock. Pythagoras or the Pythagoreans developed the circle of fifths. In music theory, the circle of fifths, going clockwise, is the relationship between the 12 primary tones or notes of the chromatic scale. They're associated sharps and flats in minor tones. The circle of fifths displays an easy method of identifying the relationship between musical notes when composing music and or tuning a stringed instrument. There are 12 points of reference that are spaced like the numbers on the face of a clock. An example of the beginning or 0 for a circle of fifths octave is primary tone F, that is at the 11 o'clock position. Primary tone C is always at the top of the circle of fifths, and the 12 o'clock position, at 12 o'clock position. Primary tone F correlates with the position of 0 for a defined color model. Primary tone C correlates with the position of the primary red anchor of the defined color model. Philosophy. Traditionally, there are 7 liberal arts, with the first 3 being logic, rhetoric, and grammar, the trivium. The other 4 are the quadrium. The quadrium divides the study of number into 4 branches: arithmetic, number in itself, and for my research, that correlates with the 1, 2, 3 color model and my concept of color math. Astronomy equals number in space and time. I've developed concepts in regards to subspace and portals. Geometry, numbers in space, the Pythagorean theorem, the color hexagram. Music or harmonics, number in time, tones, octaves, harmonics. This is a quick chart that just talks about how the circle of fifths is arranged, and I'm making correlations with the tones that are associated with the circle of fifths and the color references. From my color hexagram, the hexagram has 6 peaks, 6 valleys, and the valleys correlate with the interfaces between the 6 peaks. So I get 12 color references, which expands my color modeling a bit. I've worked with 3 color systems, red, green, blue, cyan, magenta, and yellow, or a 6-color system where you have red, green, and blue, and cyan, magenta, and yellow. And this adds another perspective to my color modeling, and that with a 12 reference points, it helped resolve a problem that I had last year when I was presenting, trying to accommodate the color orange in regards to like primary colors, that if you look at a spectral display of a prism or rainbow, it includes orange. And the question that I was trying to resolve was, is orange a primary color or is it something else? And with 12 references, it shows that orange is a interface between red and yellow. But this gets into music and the assignment of tones, and that the first part of what I'm going to address is the number correlation, and the perfect fifth is just a means of counting that you have primary tone C at the top, and F is always to the left at the 11 o'clock position. And this concept gave me a little trouble in trying to get my brain kind of wrapped around it. But what's going on is that with the circle of fifths, that it addresses a octave in all of the 12 tones, and starting with F and ending with F, I found that confusing. But what this is really telling me, and I'll get into this a little bit later, is that there are 9 musical octaves, and octave number 4 is in the middle. So in this description here, this would actually be like an F4 going to an F5, or an F4 going to an F3. And in that sense, things started to fall in line. Talking about the perfect fifth, this kind of explains what the perfect fifth is, but I need to move on. Figure 101 demonstrates a theoretical correlation of the circle of fifths to a visible light color model. The relationship is geometric. A numerical relationship was also developed. The visible light version of the circle of fifths is a harmonic of an audible sound version of the circle of fifths. The range of audible sound has approximately 14 subharmonics of the visible light primary red anchor. C major correlates with the visible light primary red anchor at 450 terahertz, or the 12 o'clock position. F major correlates with the visible light color models system 0 at approximately 427 terahertz. The magenta red interface, or 11 o'clock, or at the 11 o'clock position. So this is a combination of the circle of fifths and the color hexagram, and that it's complicated. This circle refers to the primary colors, that with the circle of constants that I use, I've identified a new family of circle of constants. This one's represented by plus or minus 10 times little phi, plus or minus 10 times 1, plus or minus 10 times big phi. And that with this setup, red and cyan is the same diameter, that green and magenta are the same diameter, and blue and yellow, excuse me, that's not correct. Yes, it is. Blue and yellow are the same diameter. And I visualize frequencies as being helixes versus sine waves. So this is a view down the x-axis, and what I see looking down the x-axis is circles. And to break this out a little bit more is that if you use a circle as in a circle of light to represent the 6 primary colors, you get this display of 6 circles around a central circle, and with the x-axis in the middle, and that my primary tones that I'm matching up to are here. And the only constraint in dividing a circle in regards to music is that it's divided in 12 equal sections, so that it's like numbers on the face of a clock. And one of the things I did was I refined my total range value for my color modeling and improved the accuracy of it, so that if you go from one edge of a circle through the center to the other side, that it not only gives you the complementary color, but it gives you the value that's 180 degrees out of phase. With music, the tone that's directly across from it is the most opposite sounding tone, but it's not necessarily complementary frequency there. Figure 101 is not a rigorous mathematical proof of a correlation between visible light and the circle of fits. It demonstrates a correlation between the geometries and the associated reference. Table 101 serves as a conversion table. Similar equations and or geometries produce similar results. Example, color to audible sound, color models. Therefore, a circle of fifths model is possible for every harmonic or subharmonic of the audible sound or visible light baseline color model. I use the method used by the A4, which is middle A, 440 method of tuning, where the 12th root of 2 is used to divide a circle into 12 equal parts in regards to on a logarithmic scale. But what I ended up doing was substituting the radicand of 2 with phi to get my modeling to work. One has a radius and the other has a radius of 2, and the other one has like a radius of phi. And this was the way I was thinking about it. The 12th root equations divide a circle into 12 equal sections or semitones on a logarithmic scale. Therefore, the 12th root equation divides the octave in the circle hexagram into 12 equal sections or a logarithmic scale. Music theory references 9 octaves, 0 to 8. Color theory references the baseline visible light primary anchor and total range values of harmonics and subharmonics. Table 201 considers the harmonic correlation of the individual F4 music octave at 349.23 hertz versus a comparable color octave. Octave F4 to octave F5 have a range of approximately 349.23 hertz. F5 is the upper limit. The comparable color octave would have a total range value of 349.23 hertz or less. The better fit is color octave phi to the 57th power. Primary rate anchor value is approximately 550.6522473 hertz with a total range value of 26.974401 hertz, which in this model, my better fit is at this point. And this is just sizing up where things fit the best. So in summary, music theory in octave is the doubling or halving of a reference frequency. The 12th root equation of the 12th root of 2 to plus or minus the x value define the equal temperament spacing of the octave. The circle of fifth represents the octave. The circle of fifth identifies the relationship between the 12 major tones. 12 major tones in sharps and flats, ordered like numbers on the face of a clock. Tones could represent notes, chords, or keys. Color theory. A harmonic is the whole number multiple or 1 over whole number multiple of a value. There are 6 primary colors with 6 interfaces per the color hexagram, which are evenly spaced and ordered like numbers on the face of a clock. Colors could represent values, events, or equations. And just to quote Aristotle, the whole is greater than the sum of its parts. I'm also working on, not struggling with, working on the concept of whole numbers being used here, because with whole numbers, fractions and decimal places are not included in regards to whole numbers. And so in talking about what is a harmonic, whether you're talking about a harmonic or subharmonic, the question comes up. What I introduced to you is something called the my Jacob's ladder. And what I want to do now is just jump around a little bit. And if I work this right, I'll be able to show you Jacob's ladder. Okay, Jacob's ladder. It's a table where my baseline that I worked with, I'm working with the golden ratio, and with the research that I've done, the golden ratio has 3 proportions. Classically, it only references big phi, little phi, but my first little phi value is here. The new value that I added was 1, and this is my first big phi value. And I'm keeping track of my exponents over here. So 1 over little phi is, you know, a negative exponent. So from here, for example, big phi times little phi equals 1. Big phi times 1 is equal to big phi. Then you go to the second power, third power, fourth power, fifth power. And going the other way, big phi times, it's little phi times big phi equals 1. Little phi times 1 equals little phi, then little phi squared, then little phi cubed to the fourth power. And I run this all the way down to where I get to the range of audible sound, which is from like 20 hertz to 20,000 hertz. And looking over to the side, that you can see where my baseline was visible light. You have ultraviolet, you have infrared. When I was looking at magnetism, I was looking at what is the Earth's magnetic fields. And that near the equator, you had 1 value, the middle ranges, middle latitudes, you had another range, and then you had another range near the poles. And you could even start seeing the a range for like electricity. And I kept going down to see how far I can go. And eventually, it seems like the time base changes from cycles per second to seconds per cycle. And eventually it goes to cycles per minute, cycles per hour, cycles per day. Next thing I want to show you is my values that I had first calculated, 9.4, 8.1, that my solution from dividing my values in regards to 1/12 versus the 12th root equation is that my zeros started in different places, and that the total range values of both systems were the same. This seemed to have been a good idea when I first started it. And so this is just a show of how the frequencies are listed within music, and that with 440 hertz being my A, that doubling that is 880, and this range identifies an octave and a rising octave, and that a lowering octave in A would be my A3, which is 220 hertz. And what I'm looking to do here is to show that my color values match up with the values of the musical tones. And I need to get to 54. In this one, my total range value is 300 terahertz, and I'll pick a spot. And this is my primary red anchor value here. This is my total range value and my upper and lower limits that are associated. But for adjacent values that I have adjacent upper and lower limits that overlap. And so this upper limit exceeds the lower limit of the higher range. And that was a flag to me to say, hey, you got a problem. Using the 12th root calculations of my primary red value, I determined what value I needed in order to establish my zeros. And it was with the 12th root equations, the 12th root of big phi to the 0 power was divided by the 12th root of big phi to the first power to give me a 0.9 value here. Where now, wherever my primary red anchor value is, times the 0.9 value gives me the lower limit value, and the lower limit value times the upper limit value proportion, the 12th root of big phi to the 12th power gives me my upper limit value. The upper limit value minus the lower limit value gives me a very close approximation of what my total range value is. And this was determined harmonically. So my harmonic value, which is, or subharmonic value in this case, is phi to the 49th power. And any frequency within this range, if it's divided by this value, will take you back to, this is the little Jacob's ladder, will take me back to my visible light color reference. and getting shorter on time, so and what this is all about, I will jump to 42. So working with my values, that with middle A, for example, and with middle C, that there's certain values that repeat, and that kind of contributes to different things tuned to different major tones sounding similar. What I was looking at was tuning something to the A or to the middle music octave, 4, versus circle of fifths. That what I found was that the interfaces all match up, and that when I got to like this one, for example, it could either be D flat or C sharp. And so again, between circle of fifths and the A440 method of tuning, all of the interfaces match up. The differences come in with the primary colors. And that assumption that I'm making right now is that based on what set of values I select for my primary colors, would say that my color space or my color mapping or my tonal mapping that I'm doing with my color modeling will either be tuned to the circle of fifths or the A44 method of tuning. And I didn't get a chance to get to the geometry, but I'm out of time. And so I'll conclude my presentation there. Thank you very much.
Thank you, Carl, for your nice presentation with colors. Any question, comments? You are welcome to directly ask the speaker. If you are from Zoom meeting, from Google meeting, or if you are on the YouTube, you can just chat. You can write it on the chat box. I can share it with the speaker. Okay, so thank you. So I get many comments like this. Thank you, nice speaker, explained well, etc. on the YouTube.
Oh, awesome. Thank you.
Yes. So I don't find any comments, any questions yet. So if not, then of course it's a time for me to say thank you to all the 3 speakers in this session. Thank you all. And maybe tomorrow we'll have again meet at the time is 4 p.m. So tomorrow at 4 p.m. we'll have day 3. So it's not day 2, but day 3. It should be day 3. And we're going to meet again here tomorrow. We're going to meet tomorrow at 4 p.m. sharp, and there will be 2 parallel sessions. So you're welcome, all welcome to that session. Thank you very much for joining us today. So see you tomorrow. So have a nice day. So good night, good evening, good morning, whatever it may be, depending on your time zone. So see you tomorrow. Bye.
Bye.
Sir, shall I stop the recording?
Yes, please.
Okay.
Okay. Then, good night.